Hello there, and welcome to Science for Sleep, the little corner of the universe where curiosity slows its pace. Thoughts soften their edges, and the night becomes a gentle place to wander through ideas instead of worries. Wherever you happen to be listening from right now, whether it is late evening with the lights turned low, early morning with the sky just beginning to shift colours, or some quiet moment in between, I am glad you found your way here. Before we drift too far into the stars, take a second to notice where you are. The room around you, the way you're sitting or lying down, the steady rhythm of your breathing. It is a small, calm point in a very large universe. Tonight, we are going to talk about something so enormous that even the word big feels a little underqualified. We're going to explore a place where light struggles to escape, where matter moves in ways that stretch the rules we're used to, and where distance itself starts to feel like a suggestion rather than a measurement. Our focus will be on a black hole called TON 618, a name that sounds more like a quiet code than one of the most massive objects ever discovered. And guiding our view tonight is a telescope that does not just look at the universe, but listens to its warmth, its dust, and its faint, ancient glow. The James Webb Space Telescope. Before we begin, let me ask you something simple and personal. What time is it where you are right now? Not just the number on a clock or a phone screen, but the feeling of the moment. Is it the kind of time that feels heavy with the day that just ended, or light with the promise of rest ahead? Are you listening from a city where the hum of distant traffic never fully fades, or from somewhere quieter, where the loudest sound might be the soft movement of air or a ticking clock in another room? If you find this slow journey through space and science calming, interesting, or just a nice way to let your thoughts settle, you can gently tap the like button or subscribe to this channel. It helps this small, quiet project reach other people who might also be looking for a peaceful way to end their day or begin their night. There is no rush. Nothing here is urgent. The universe has been waiting for billions of years. It can wait a little longer for us to get comfortable. So take a slow breath in and let it out without trying to control it. Let your shoulders drop just a bit. We are not going to race through facts or chase dramatic moments. Instead, we're going to ease our way outward from this small, familiar place to a region of space so distant and so extreme that even our best instruments are only just beginning to make sense of it, far beyond the reach of any human spacecraft, past the bright neighbourhoods of nearby stars, past galaxies that appear as faint smudges even in powerful telescopes. There is a point of darkness that does not glow, does not shine, and does not announce itself in the way stars do. It reveals its presence by what it does to everything around it. This is where our story begins. Imagine a region of space that looks, at first glance, like nothing at all. No sparkling points of light, no colourful clouds of gas, no obvious landmarks. Just a quiet, deep patch of darkness set against the faint glow of the distant universe. But this darkness is not empty. It is full of motion, heat, and force so strong that even light, the fastest traveller we know, cannot simply pass through and keep going. This is where TON 618 lives. TON 618 is what astronomers call a supermassive black hole, though even that phrase feels almost casual for something of its scale. It sits at the centre of a quasar, which is a type of galaxy core that shines so brightly it can outshine the entire galaxy around it. That light does not come from the black hole itself, because black holes do not emit light in the usual way. Instead, it comes from a vast disk of gas and dust that spirals around the black hole, heating up as it falls inward, glowing across enormous distances of space. To understand why TON 618 is so special, it helps to step back and think about what a black hole actually is, in simple terms. A black hole forms when a large amount of mass is squeezed into a very small space. Gravity, which is the force that pulls things together, becomes so strong in that region that nothing can escape once it gets too close. Not light, not particles, not even information as far as we currently understand. There is a boundary around every black hole called the event horizon. This is not a physical surface like the ground beneath your feet. It is more like a point of no return. If something crosses that invisible line, it cannot come back out. From the outside, we can never see what happens beyond it. We can only observe the effects on the surrounding space. Most black holes we hear about in everyday science news are created when massive stars collapse at the end of their lives. These are called stellar mass black holes, and they can be several times more massive than our Sun. They are impressive, powerful, and strange. But they are small compared to what sits at the centres of galaxies. Supermassive black holes like TON 618 are in a different category entirely. They can be millions or even billions of times more massive than the Sun. They do not form from a single collapsing star. Their origins are still one of the big open questions in astronomy. Did they grow slowly over time, feeding on gas and stars? Did they form very early in the universe from huge clouds of collapsing matter? Or is the answer a mix of both? TON 618 pushes these questions to their limits. This black hole is estimated to have a mass of about 66 billion times the mass of our Sun. To put that into perspective, if you took every star in our solar system, added them together, and then multiplied that total tens of billions of times, you would start to approach the mass of this single object. Its event horizon, the boundary beyond which nothing returns, is so large that if you placed it at the centre of our solar system, it would extend far beyond the orbit of Neptune. And yet, despite this scale, TON 618 is incredibly far away. The light we see from its quasar has been travelling toward us for more than 10 billion years. That means we're not seeing it as it is now. We're seeing it as it was when the universe was much younger, when galaxies were still forming and growing into the shapes we recognise today. For a long time, astronomers studied TON 618 using telescopes that detect visible light and some forms of infrared. They could measure how fast the gas in its accretion disk was moving, how bright the quasar appeared, and how its light was stretched and shifted by the expansion of the universe. These measurements gave them a rough idea of its mass and size. Even then, it stood out as one of the largest known black holes. But rough ideas are not the same as detailed understanding. This is where the James Webb Space Telescope enters the picture. Unlike earlier space telescopes, which focused mainly on visible and near-infrared light, James Webb is designed to look deeper into the infrared. This allows it to see through dust clouds that would otherwise block our view. It can detect heat signatures from objects that are too cool or too distant to glow brightly in visible light. In a sense, it does not just see the universe, it feels it. When astronomers turned Webb's instruments toward distant quasars, like the one powered by TON 618, they were not just hoping for prettier pictures. They were looking for more precise data. They wanted to measure the structure of the gas and dust around the black hole, the way that material moves, the temperatures it reaches, and the way energy flows through this extreme environment. What they found began to refine, and in some ways expand, our sense of scale. One of the challenges in understanding a black hole like TON 618 is that we cannot see the black hole itself. We infer its properties by watching how it affects its surroundings. The faster gas moves, the stronger the gravity must be. The brighter the accretion disk, the more material is falling in and heating up. The shape of the light spectrum tells us about temperature, composition, and motion. Webb's ability to separate different wavelengths of infrared light with high precision allows astronomers to map these regions in more detail than before. They can distinguish between hot, fast-moving gas close to the event horizon and cooler, slower material farther out. They can see how dust is distributed around the quasar and how it absorbs and re-emits energy. This matters because scale is not just about size in kilometers or miles. It is also about layers, structure, and relationships. It is about how far the influence of the black hole extends into its host galaxy. It is about how much energy it pumps into its surroundings. It is about how it might shape the growth of the galaxy itself. As these new observations came in, astronomers began to refine their models of TON 618's environment. The accretion disk appeared even more extended and energetic than earlier data had suggested. The region of space influenced by the black hole's gravity and radiation seemed to reach farther into the surrounding galaxy than expected. This does not mean that the basic mass estimate of TON 618 suddenly doubled or changed dramatically. Science rarely works in sudden leaps like that. Instead, it is more like adjusting the focus on a camera. The object was always enormous, but now its edges, its structure, and its impact are coming into sharper view. To really appreciate what this means, it can help to compare TON 618 to something more familiar. Our Sun is about 1.4 million kilometers across. Light takes about 8 minutes to travel from the Sun to Earth. The distance from the Sun to the edge of our solar system, to a region called the heliopause, is so large that even our fastest spacecraft would take tens of thousands of years to reach it. Now imagine a black hole whose event horizon alone is larger than the entire solar system. Not the region influenced by its gravity, but just the boundary where escape becomes impossible. Around that, imagine a disk of glowing, superheated gas that extends for distances that make our familiar planetary orbits look like small marks on a page. And then imagine that this entire structure is sitting in a galaxy so far away that its light began its journey toward Earth before our planet even existed. This is the scale we're talking about. When James Webb observes such a distant object, it is not just collecting photons, it is collecting history. Every bit of light and heat it detects has travelled across an expanding universe, passing through space that has stretched and changed over billions of years. By the time it reaches Webb's instruments, it carries information about conditions that no longer exist in the same form. This adds another layer to the idea of scale. TON 618 is not just large in space, it is also large in time. It represents an era in the universe's development when supermassive black holes were growing rapidly, when galaxies were colliding and merging, when vast amounts of gas were available to fuel these cosmic engines. One of the questions that naturally arises is how something like TON 618 could have grown so big, so fast. The universe was only a few billion years old when the light we now see from it was emitted. That is not a lot of time, in cosmic terms, to build a black hole tens of billions of times more massive than the Sun. Webb's observations help here as well. By looking at the properties of the surrounding galaxy and the material feeding the black hole, astronomers can estimate how efficiently TON 618 is converting and falling matter into energy. They can look for signs of past mergers with other galaxies or black holes. They can study the chemical composition of the gas, which hints at how many generations of stars lived and died before this quasar reached its current state. All of this feeds into a bigger picture of how structure forms in the universe. There is something quietly humbling about this process. We build instruments with mirrors larger than any launched before. We send them millions of kilometers away from Earth. We cool them to temperatures just above absolute zero. And even then, what we get back are still indirect clues, patterns in light and heat that we have to interpret carefully. TON 618 remains, in many ways, a silhouette. A powerful one, yes, but still a shape defined by what surrounds it, rather than by any direct image of its core. As you let this settle in, you might notice a strange shift in perspective. The things that feel large in everyday life, buildings, mountains, even continents, start to shrink a little in your mind. The span of a human lifetime, which can feel so long when you're in the middle of it, becomes a brief moment compared to the age of the light coming from this distant quasar. This is not meant to make anything feel small in a negative way. It is more like opening a window in a room you've been in for a long time. The room is still there, it still matters. But now you can also see the landscape beyond it. There is a quiet connection here between the technology we build and the curiosity that drives us to use it. James Webb is, in a very real sense, an extension of the same impulse that leads someone to look up at the night sky and wonder what is out there. The difference is that now, that wondering is paired with instruments that can reach across billions of years. For now, though, it is enough to sit with the idea of this distant, powerful presence. A region of space where matter moves in long, spiralling paths, heating up, glowing, and finally disappearing past a boundary we cannot cross or see beyond. Somewhere out there, long before life appeared on Earth, gas was falling into this black hole. Light was being released. That light began a journey that would take it across an expanding universe, past forming galaxies, past stars that would live and die, past a small planet that would eventually become home to people who build telescopes and tell stories about what they find. And now, quietly, without any fanfare, that light is being turned into data, images and numbers that help us understand just how vast and layered the universe really is. Somewhere between the numbers on a page and the pictures in our minds, there is a quiet gap where understanding starts to wobble. That is usually where objects like TON 618 live, not because they are hidden, but because they are so far beyond everyday experience that the usual mental tools we use to picture things begin to feel a little inadequate. So instead of trying to grasp it all at once, it helps to move slowly, building a sense of this black hole piece by piece, like walking around a very large structure rather than trying to take it in from a single glance. Let's begin with the name itself. TON 618 does not have a poetic or dramatic title. It does not carry the name of a mythological figure or a sweeping phrase about darkness or infinity. It comes from a catalogue. Specifically, it was first identified in the Tenantzintla Observatory catalogue in Mexico, which is where the TON part comes from, and the number simply marks its place in that list. This plain, almost administrative name hides the fact that what it refers to is one of the most extreme objects ever observed. At first, astronomers did not even know they were looking at a black hole. What they saw was a quasar, a point of light in the sky that looked like a star through early telescopes but behaved very differently. Quasars are among the brightest objects in the universe. Some of them shine with the energy output of hundreds or even thousands of galaxies combined, and yet they are powered by something that itself does not emit light in the usual sense. This is one of the small but important paradoxes of black holes. On their own, they are dark. But the process of feeding them can light up the universe. In the case of TON 618, the quasar it powers is so luminous that it can be detected across billions of light years. The light we see from it today began its journey when the universe was less than a third of its current age. Back then, galaxies were closer together, gas was more abundant, and the conditions were right for black holes to grow quickly. To understand what makes TON 618 a colossus, we need to talk about how astronomers measure the mass of something they cannot see directly. There is no scale you can place under a black hole. There is no surface you can observe or boundary you can mark with a ruler. Instead, mass is inferred from motion. Everything near a massive object feels its gravity. The stronger the gravity, the faster nearby material has to move to avoid falling in. By observing how fast gas and stars are moving around a black hole, astronomers can work backward to calculate how much mass must be pulling on them. For TON 618, this is done by studying the light from its accretion disk, the vast rotating structure of gas and dust that spirals inward toward the event horizon. This disk emits light across a range of wavelengths. When that light is split into a spectrum, it reveals signatures of different elements and, crucially, how fast they are moving toward or away from us. This motion causes a shift in the light's wavelength, known as the Doppler effect. If the gas is moving toward us, the light is shifted slightly toward the blue end of the spectrum. If it is moving away, it shifts toward the red. By measuring the width of these spectral lines, astronomers can estimate the speed of the gas in the disk. Faster motion means stronger gravity. Stronger gravity means more mass. When these calculations were first applied to TON 618, the results were already staggering. Early estimates placed its mass at tens of billions of times that of the Sun. As methods improved and new data came in, those estimates were refined. but they remained in the same extraordinary range. Even among supermassive black holes, TON 618 stood near the top of the list. To give this some context, the black hole at the centre of our own galaxy, the Milky Way, has a mass of about 4 million suns. That is already considered supermassive. TON 618 outweighs it by a factor of more than 10,000. This difference is not just a matter of size, it represents a completely different scale of influence. The black hole in our galaxy quietly shapes the orbits of stars near the galactic centre. It does not dominate the entire Milky Way. It is one player among many in a vast system of stars, gas and dark matter. TON 618, by contrast, is thought to have a much more dramatic relationship with its host galaxy. The energy released by its quasar can heat and push away gas on galactic scales. This can slow or even stop star formation in large regions. In this way, the black hole does not just sit at the centre of its galaxy, it helps determine how that galaxy evolves. Now let's talk about the size of the event horizon, because this is where the numbers start to feel especially strange. The radius of a black hole's event horizon is directly related to its mass. For a non-rotating black hole, this is called the Schwarzschild radius. The formula is simple enough on paper. In practice, the results can be hard to picture. For a black hole with the mass of the Sun, the event horizon would be about 3 kilometres across. That means you could, in theory, compress the entire Sun into a sphere smaller than a city, and it would become a black hole. Scale that up to TON 618, and the event horizon becomes enormous. Its diameter is estimated to be on the order of hundreds of billions of kilometres. If you placed it at the centre of our solar system, its edge would extend far beyond the orbit of Pluto. This does not mean that space suddenly ends at that boundary. You would not see a solid surface or a glowing wall. You would cross the event horizon without noticing anything special at the moment you passed it. From your perspective, nothing would change immediately. From the outside, however, you would appear to slow down and fade as your light struggled to escape. The sheer size of this boundary is what earns TON 618 its reputation as a colossus. It is not just massive in terms of weight. It occupies an immense volume of space where the rules of motion and time are deeply altered. Another way to approach this is to think about the accretion disk. This is not a thin, flat ring like the ones around Saturn. It is a thick, turbulent structure, more like a swirling, glowing cloud shaped into a rough disk by rotation and gravity. For TON 618, this disk extends for distances that make the event horizon itself look small by comparison. The inner regions are incredibly hot, emitting intense radiation as gas falls inward and releases gravitational energy. Farther out, the disk cools, and dust can survive, re-radiating energy in the infrared. This is one of the reasons the James Webb Space Telescope is so useful for studying such objects. It can detect the infrared glow of this dust, allowing astronomers to map regions of the disk and surrounding structures that were previously hidden. What makes this particularly interesting is that the structure of the disk can tell us something about how the black hole is being fed. Is the gas flowing in smoothly, or is it arriving in clumps? Is the disk stable, or is it warped and disturbed by past interactions with other galaxies or black holes? In the case of TON 618, the environment appears complex and energetic. The quasar's brightness suggests that the black hole is still actively accreting large amounts of material. This means it is not just a relic of the early universe. It is still growing, even now. This raises a quiet but persistent question. How big can a black hole get? There is a theoretical limit to how fast a black hole can grow through steady accretion. If too much material falls in too quickly, the energy released can push away incoming gas, slowing the growth. This is known as the Eddington limit. It acts like a kind of balance point between gravity pulling matter in and radiation pushing it out. TON 618 appears to be close to this limit, which suggests that it has been feeding efficiently for a very long time. To reach its current mass, it would have needed a steady supply of gas over billions of years, or a series of mergers with other massive black holes, or both. Webb's observations help astronomers look for clues about this history. By studying the chemical makeup of the gas around the quasar, they can infer how many generations of stars have lived and died in that region. Heavy elements like carbon, oxygen, and iron are produced in stars and spread through space when those stars explode. A high abundance of these elements suggests a long history of star formation and enrichment. This, in turn, provides a timeline for the galaxy's development and the black hole's growth. It is like reading layers in a rock formation, but instead of stone, the layers are written in light and heat. Another aspect of TON 618's scale is its distance. When we say it is billions of light years away, that is not just a measure of how far its light has travelled. It is also a measure of how much the universe has changed in the meantime. As light travels through space, the space itself is expanding. This stretches the light's wavelength, shifting it toward the red end of the spectrum. This is called redshift. The amount of redshift tells astronomers how fast the universe was expanding when the light was emitted, and, by extension, how far away the source is. TON 618 has a high redshift, which places it in a period of cosmic history when galaxies and black holes were in a phase of rapid growth. Studying objects from this era helps astronomers understand how the large-scale structure of the universe came to be. There is something quietly remarkable about the fact that we can sit in a room on Earth, look at a screen, and see data from an object that existed in a very different version of the universe. The air around us, the planet beneath us, the sun in our sky. None of these were around when the light we are now detecting left. TON 618. This makes the black hole not just a distant object, but a kind of time marker. It is a window into a period of cosmic history that we cannot otherwise visit. As you consider this, it can help to think about how fragile and specific our perspective is. We see the universe from one place, at one time, with a particular set of tools and assumptions. TON 618 does not exist for us as a physical thing we could ever approach or touch. It exists as patterns in data, as curves on graphs, as images built from infrared signals translated into colours we can see. And yet, from these abstractions, we build a picture of something real, massive, and powerful. One of the quieter insights that comes from studying such extreme objects is how connected everything is across scale. The same laws of physics that govern a cup of water swirling in a sink also govern gas spiralling into a black hole billions of times more massive than the Sun. The equations look different on the page because the numbers are so much larger, but the underlying relationships are the same. Gravity pulls, motion responds, energy is released. This continuity is part of what makes science feel grounded, even when it deals with things that feel far removed from everyday life. TON 618 is not a fantasy or a metaphor. It is a physical system, governed by the same principles that keep your feet on the floor and the moon in orbit around Earth. As Webb continues to collect data, astronomers are refining their understanding of how the black hole's mass is distributed and how its surrounding structures behave. There are hints of complex motions in the gas, possibly influenced by interactions with other galaxies in the past. There are signs of powerful outflows, streams of material being pushed away from the quasar by intense radiation. These outflows are another way the black hole makes its presence felt far beyond its immediate neighbourhood. They can carry energy and material into the wider galaxy, shaping the environment where new stars might form. So when we call TON 618 a colossus, we are not just talking about a large object sitting quietly in space. We're talking about a system that operates on multiple scales at once. It has a central region where gravity dominates completely. It has a surrounding disk where matter moves at incredible speeds and temperatures. It has an influence that can extend across an entire galaxy. And all of this is happening in a part of the universe that we can only see, because light, stretched and cooled by billions of years of travel, finally reaches our detectors. There is a subtle shift that can happen when you spend time thinking about something like this. The usual sense of up and down, near and far now and then begins to soften. The idea that an object so distant and so ancient can still affect what we learn and how we think, today creates a kind of quiet continuity between past and present. We are not just observers looking out at a frozen picture of the universe. We are part of an ongoing process of discovery, where each new instrument adds another layer of detail to a story that has been unfolding since long before there were any minds to notice it. How does a telescope in space translate infrared light into estimates of mass, speed, and structure? What assumptions go into those models, and where do the uncertainties remain? There is a point when you start thinking about objects like TON 618, where the mind naturally looks for something familiar to hold on to. A mountain, an ocean, a planet. Something with edges and surfaces and a sense of here and there. That instinct makes sense. Most of what we deal with in everyday life fits into a scale where comparison works. A room is bigger than a chair. A city is bigger than a room. A continent is bigger than a city. The ladder of size feels orderly, but TON 618 does not sit comfortably on that ladder. It does not just occupy a higher rung, it stretches the ladder itself. One of the main reasons this black hole has always been hard to imagine is that it lives in a category of objects that we do not have any direct sensory experience with. You have never seen something that bends space and time in a noticeable way. You have never watched light fail to escape from a region in front of you. Gravity in daily life is gentle and predictable. You drop something, it falls. You jump, you come back down. The idea that gravity can become so strong that even light cannot leave feels less like an extension of that experience, and more like a different rule entirely. So when people hear that TON 618 is tens of billions of times more massive than the Sun, the number itself often floats past without landing. It is technically precise, but emotionally vague. A billion is already an abstract idea for most of us. Tens of billions applied to something we cannot see or touch pushes the concept even farther from intuition. Another layer of difficulty comes from the fact that a black hole is not a thing in the way most objects are things. A star has a surface, even if it is a glowing, turbulent one. A planet has a shape you can draw. A galaxy has arms and a centre and a visible structure. A black hole, at least as we understand it, is defined more by a boundary than by a body. The event horizon is not made of material. It is not a shell or a wall. It is a mathematical surface, a point in space where the escape velocity becomes greater than the speed of light. That means that imagining the size of a black hole is not like imagining the size of a ball or a building. It is more like imagining the size of a region where a rule changes. For TON 618, that region is enormous, but it's still just a region. The mass itself is thought to be concentrated in a volume far smaller, possibly compressed into a point according to our current theories. This creates a strange mismatch between what is physically there and what we talk about when we describe its size. In everyday language, size usually refers to how much space something takes up. With black holes, size often refers to the reach of their influence, not the extent of their material. That is a subtle but important shift, and it makes mental pictures harder to build. There is also the challenge of distance. TON 618 is not just large. It is far away in a way that does not map neatly onto human experience. We're used to thinking in terms of kilometres or miles. Maybe on a more adventurous day we think in terms of the distance between Earth and the Moon, or Earth and the Sun. A light year, the distance light travels in a year, is already a step beyond that. About 9.46 trillion kilometres. That is a number that can be written down, but not really felt. TON 618 is billions of light years away. At that scale, distance stops being about travel time in any practical sense and becomes more like a measure of history. When you look at it, you're not just looking across space. You're looking back in time to an era when the universe itself was younger and structured differently. This adds another layer of abstraction. You're not imagining an object as it is now. You're imagining an object as it was long before you, or anyone else existed. That temporal separation can make the black hole feel more like a concept than a place. It is something inferred from data, reconstructed from signals that have crossed an evolving universe, rather than something that feels present in the same way the moon or the sun feels present. Even the tools we use to study TON 618 contribute to this sense of distance from everyday reality. The James Webb Space Telescope does not take pictures in the way a phone camera does. It detects infrared light and converts it into data. That data is processed, corrected, and often translated into colours that represent different wavelengths or intensities. The final images are not what it looks like in a simple sense. They are visualizations, designed to help human eyes and brains interpret patterns in radiation. So when you see a representation of a distant quasar or galaxy, you're not seeing a snapshot in the usual way. You're seeing a map of energy, carefully turned into something that fits our visual language. This makes the experience of learning about TON 618 one step removed from direct observation. It is always mediated, always filtered through instruments, models, and choices about how to present information. Another reason this black hole resists imagination is that it challenges our sense of scale in multiple directions at once. On the one hand, it is incredibly compact in terms of mass. All that material, tens of billions of suns worth, is thought to be concentrated into a region that, in some theoretical descriptions, has no volume at all. On the other hand, the region of space where its presence dominates, the event horizon and beyond, is vast. This combination of extreme density and extreme reach is not something we encounter anywhere else. A mountain is large because it is made of a lot of material spread over a wide area. A black hole is influential because it is made of a lot of material squeezed into a very small area. Trying to hold both of those ideas at the same time can feel like trying to imagine something that is both tiny and enormous in the same breath. There is also the issue of behaviour. Objects in everyday life behave in ways that feel consistent. If you push something, it moves. If you heat something, it gets warmer. With black holes, behaviour crosses into a regime where familiar ideas start to bend. Time itself is affected by gravity. Near a massive object like TON 618, time would pass more slowly compared to a region farther away. That is not just a figure of speech. It is a measurable effect, one that has been confirmed on much smaller scales around Earth. Light does not travel in straight lines near a black hole. Its path curves as space itself curves. This means that the black hole can act like a lens, distorting and magnifying the light of objects behind it. These effects are real, but they are not part of everyday intuition. They belong to a layer of reality that we usually only encounter through equations and simulations. So when someone tries to picture TON 618, they are not just picturing a large object. They are trying to picture a region of space where the rules they live by quietly change. Another subtle difficulty comes from language itself. Words like mass, size, and gravity carry everyday meanings that do not quite fit the way those concepts work in extreme astrophysical contexts. Mass in daily life is often associated with weight. You pick something up and you feel how heavy it is. But in space, weight depends on gravity. Mass is about how much matter something contains and how strongly it influences other things through gravity. TON 618's mass does not make it heavy, in the sense that you could feel its weight. There is nothing there to stand on. Its mass shows itself through the motion of gas, the bending of light, and the structure of its host galaxy. Size, as mentioned before, does not refer to a physical body in the usual way. It refers to a boundary in space-time. Even location becomes a bit strange. A black hole is not just sitting in space like a chair in a room. It is part of the structure of space itself. The space around it is shaped by its presence. All of this means that when we talk about TON 618, we're using everyday words to point at ideas that live outside everyday experience. That can make the picture feel fuzzy, no matter how carefully it is described. There is also the challenge of comparison. The human brain is very good at understanding things by comparing them to other things. This is bigger than that. This is farther than this. This is heavier than that. With TON 618, the usual reference points run out quickly. There are only a handful of black holes known to be in the same general class of mass. Even those are still estimates, with uncertainties and ongoing debates. So when we say TON 618 is among the largest known, we are not ranking it in a well-populated list. We are placing it near the top of a very short and still growing category. This can make its record-breaking status feel less concrete. It is not like comparing the height of mountains on Earth, where there are many to choose from, and the differences can be measured precisely. It is more like comparing a few distant silhouettes in a fog and trying to decide which one is tallest. The fog, in this case, is made of limited data, vast distances, and complex models. Another aspect that makes TON 618 hard to imagine is how little of it we can ever directly observe. We do not see the black hole. We see the effects of the black hole on the material around it. That material is often in violent motion. Gas in the inner parts of the accretion disk can reach a significant fraction of the speed of light. Temperatures can rise to millions of degrees. Radiation can be intense enough to strip electrons from atoms and create powerful streams of charged particles. This is not a calm, static scene. It is a dynamic, energetic environment that changes over time. Yet, when we talk about TON 618, we often present it as a single, stable object. That is another simplification that can hide as much as it reveals. The black hole itself may be stable on long timescales, but its surroundings are anything but. This contrast between a central region of extreme gravity and a surrounding region of intense motion and radiation can be hard to hold in a single mental image. It is like trying to picture a still point inside a storm that never quite settles. There is also the matter of scale within scale. The galaxy that hosts TON 618 is itself a massive structure, containing billions of stars, clouds of gas, and vast amounts of dark matter. That galaxy exists within a larger web of galaxies, connected by filaments of matter that stretch across millions of light years. So TON 618 is not just large in isolation. It is large within a system that is already unimaginably large. This nested structure can make the mind feel like it is constantly zooming in and out, never quite settling at a comfortable level of detail. One moment, you're thinking about the event horizon of the black hole, a boundary that could swallow entire solar systems. The next, you're thinking about the cosmic web, a structure so large that individual galaxies become small points within it. TON 618 sits somewhere in the middle of that range, linking the very small and the very large through gravity. Another reason this black hole has always been hard to imagine is that it touches on the limits of our current understanding. Black holes, especially at this scale, are places where our best theories, general relativity and quantum mechanics, do not fully agree. We can describe how gravity behaves around the black hole. We can model the motion of gas and light. But when it comes to what happens at the very centre, our equations break down. This means that part of TON 618 is not just unseen. It is, in a sense, unknown. We can make educated guesses, propose theories and run simulations, but we do not have a complete tested description of the physics at work in the most extreme regions. That uncertainty can make the object feel more like a mystery than a place. It is something that marks the edge of what we know, rather than something that fits neatly within it. There is also a psychological element to this. The human brain evolved to deal with environments on the scale of meters and kilometers, seconds and years. It did not evolve to deal with billions of years and billions of light years. When confronted with numbers and concepts at that scale, the brain often responds by turning them into symbols rather than experiences. Billions becomes a label rather than a quantity. Cosmic becomes a general category rather than a specific size. This is not a failure of intelligence. It is simply a reflection of the environments we are adapted to navigate. Learning about TON 618, then, often involves a kind of translation. Scientists translate data into models, communicators translate models into language, listeners translate language into mental images. At each step, something is simplified, something is emphasized, and something is left out. The result is a picture that is useful and meaningful but never complete. And yet, even with all these barriers to imagination, there is something about TON 618 that continues to draw attention. Part of it is the sheer extremity of the object. Part of it is the way it sits at the intersection of so many big questions. How did the first black holes form? How did they grow so large so quickly? How do they influence the galaxies around them? What happens to information that falls into them? How do space and time behave at their centres? TON 618 does not answer these questions by itself, but it provides a powerful test case. It is an example of what the universe can build when conditions allow for long-term, large-scale growth under the influence of gravity. As the James Webb Space Telescope and other instruments continue to observe it, the picture will likely become more detailed, and in some ways more complex. New features may be discovered, old assumptions may be revised, estimates may shift. This process of gradual refinement is part of what makes the object hard to pin down in the imagination. It is not a fixed target. It is a subject of ongoing study. There is a quiet parallel here between the way TON 618 resists simple description and the way the universe itself often does. We build stories, models, and images to make sense of what we find. Those tools work well within certain ranges, but when we push them to the extremes, they start to show their limits. Thinking about this black hole can, in a gentle way, highlight those limits. It can remind you that understanding is often a matter of approximation, not capture. We circle around an idea, adding details, refining perspectives, rather than grabbing hold of it all at once. How did early measurements shape the picture? What assumptions were built into those models? Where were the biggest uncertainties? Long before the James Webb Space Telescope ever unfolded its mirrors in the cold quiet of space, TON 618 already had a reputation. It was known as one of the giants, a black hole that appeared again and again in papers, charts, and lists of largest known. But what it meant to know something like that, at such a distance and at such a scale, was always a little more tentative than the confident phrasing suggested. The picture astronomers had of TON 618 before Webb was built from layers of indirect evidence. It was not a portrait. It was more like a sketch drawn from shadows, motions, and faint signals stretched thin by time and distance. To understand what that picture looked like, it helps to start with how TON 618 first entered the scientific record. It was identified in the mid-20th century as a bright point of light that did not behave like an ordinary star. Its spectrum showed strong emission lines, signatures of hot gas moving at high speeds. Its brightness did not fade the way a star's might if it were simply far away. Instead, it hinted at an enormous energy source. As the concept of quasars became clearer, TON 618 found its place among them. Astronomers realized that these strange, bright objects were not stars at all, but the active centers of distant galaxies, powered by supermassive black holes pulling in vast amounts of material. From that point on, TON 618 was studied through the tools available at the time, ground-based telescopes, and later space telescopes like Hubble, collected light in visible and near-infrared wavelengths. That light was split into spectra, analysed for shifts and shapes, and turned into estimates of speed, distance, and mass. The process was careful, but it always came with uncertainties. One of the main challenges was brightness. TON 618's quasar is extremely luminous. That sounds like it would make it easy to study, but in practice, brightness can be a double-edged sword. The intense radiation from the inner regions of the accretion disk can overwhelm fainter signals from surrounding structures. It can mask details rather than reveal them. So the early view of TON 618 was dominated by what could be learned from the broad strokes of its light. Astronomers measured how wide the emission lines in its spectrum were. They used those widths to estimate how fast the gas in the accretion disk was moving. From those speeds, they inferred the strength of the gravitational pull at the centre. From that, they calculated the mass. This method, known as reverberation mapping and related techniques, relies on a chain of assumptions. It assumes a certain geometry for the disk. It assumes that the gas is moving in a roughly predictable way. It assumes that the light we see reflects the conditions close to the black hole, rather than being heavily altered by dust and gas farther out. For many objects, these assumptions work reasonably well. For something as extreme as TON 618, they introduce larger margins of error. So even before Webb, there was a range rather than a single precise number attached to its mass. Estimates clustered around the idea that it was tens of billions of times more massive than the Sun, but the exact figure varied from study to study. Despite this uncertainty, one conclusion remained steady. Whatever the precise number, TON 618 was among the most massive black holes known. The early picture of its environment was similarly broad. Astronomers knew it was surrounded by a bright accretion disk, and that this disk was feeding a powerful quasar. They knew that there was dust and gas in the surrounding galaxy, because the light from the quasar was partially absorbed and re-emitted at different wavelengths. But the details of that structure were blurry. Dust in particular was a persistent obstacle. Interstellar dust absorbs visible light and scatters it. This can make regions of a galaxy appear darker, or can hide entire structures from view. Infrared light, which has longer wavelengths, can pass through dust more easily. But earlier infrared instruments did not have the sensitivity or resolution that Webb now provides. So the pre-Webb understanding of TON 618's surroundings was shaped by what could be seen through this dusty veil. Astronomers knew there was more there. They just could not see it clearly. There was also the challenge of resolution. TON 618 is so far away that even powerful telescopes cannot resolve its host galaxy into fine detail. The galaxy appears as a small, faint shape, and the quasar at its centre dominates the light. This meant that studies of the galaxy itself, its size, its structure, and its interaction with the black hole, were limited. Researchers could estimate its mass and star formation rate in broad terms, but not map its features the way they can for closer galaxies. So before Webb, TON 618 was often treated as a kind of point source with an enormous gravitational signature, rather than as part of a richly detailed system. Another part of the early picture involved comparison. TON 618 was often discussed alongside other massive black holes discovered in distant quasars. By placing it in a group, astronomers could look for patterns. Did the largest black holes tend to appear at certain distances? Did they share similar properties in their spectra? Did their host galaxies have common features? From these comparisons, a general narrative emerged. In the early universe, black holes grew quickly. There was more gas available. Galaxies collided and merged more often, funneling material toward their centres. This allowed some black holes to reach enormous sizes in a relatively short cosmic time. TON 618 was seen as one of the most extreme examples of this process. But the details of how it fit into that story were still open to debate. Was it a rare outlier, or just the most visible member of a larger population that we had not yet fully detected? Was its growth steady, or did it experience bursts of rapid feeding separated by quieter periods? The data available before Webb could hint at answers, but not settle them. One of the more intriguing questions was how efficient TON 618's accretion process was. The brightness of the quasar suggested that a significant fraction of the energy from infalling matter was being converted into radiation. This efficiency can be influenced by the black hole's spin. A rapidly spinning black hole can, under certain conditions, extract more energy from the accretion process. So there were attempts to estimate the spin of TON 618, based on the shape of its spectrum and the way its brightness varied. These attempts were necessarily indirect, and came with large uncertainties. But they added another layer to the picture. TON 618 might not just be massive, It might also be a fast spinner, a kind of cosmic engine operating near its theoretical limits. The variability of the quasar was another piece of the puzzle. Quasars can change in brightness over time as the flow of gas into the black hole fluctuates. By monitoring these changes, astronomers can learn about the structure of the accretion disk and the size of the region where the light is produced. For TON 618, some variability was observed, but the timescales involved were long, partly because of its immense size and partly because of the way time is stretched by the black hole's gravity and the expansion of the universe. This made it harder to use variability as a precise tool for mapping its inner regions. Another part of the pre-Webb understanding came from radio observations. Some quasars produce powerful jets of charged particles that shoot out from their centres at near-light speeds. These jets can extend for hundreds of thousands of light-years and are visible in radio wavelengths. TON 618 does not have especially prominent jets compared to some other quasars, but radio studies still provided information about its broader environment. They hinted at interactions between the quasar's energy output and the surrounding galaxy, such as regions where gas might be heated or pushed away. These observations contributed to the idea that TON 618 was not a passive object. It was actively shaping its host galaxy, even if the exact mechanisms were not fully clear. So by the time Webb was launched, the general outline of TON 618 was something like this. It was a distant quasar, located billions of light-years away, shining brightly from the centre of a galaxy in the early universe. It was powered by a supermassive black hole with a mass on the order of tens of billions of suns. It had a large, energetic accretion disk and was surrounded by dust and gas that absorbed and re-emitted its radiation. Its gravity and energy output likely influenced the evolution of its host galaxy, possibly regulating star formation by heating or expelling gas. This picture was impressive, but it was also broad and in places blurry. It was based on models that worked well in general, but were stretched to their limits by the extreme nature of the object. There were also open questions about the galaxy itself. How massive was it compared to the black hole? In many nearby galaxies, there is a rough correlation between the mass of the central black hole and the mass of the galaxy's bulge. TON 618 appeared to challenge that relationship. Its black hole seemed disproportionately large compared to what was inferred about its host galaxy. This raised the possibility that in the early universe, black holes and galaxies did not always grow in lockstep. Perhaps black holes could outpace their hosts, growing faster than the surrounding stars could form. But again, this conclusion depended on estimates of the galaxy's mass and structure that were themselves uncertain. The dust around TON 618's galaxy also complicated matters. Dust can hide star formation. A galaxy might be forming stars at a high rate, but if much of that activity is buried in dusty regions, it will not show up clearly in visible light. Instead, it will glow in the infrared. Without detailed infrared observations, astronomers could not be sure whether the host galaxy was relatively quiet or actively building new stars behind a veil of dust. This is one of the places where the limitations of pre-Webb instruments were most keenly felt. Infrared telescopes existed, but they did not have the combination of sensitivity and resolution needed to disentangle the different components of such a distant, complex system. So the early understanding of TON 618 was, in many ways, a story of inference. Scientists took what they could measure directly, such as spectral lines and overall brightness, and used theoretical models to fill in the rest. These models were grounded in physics that had been tested in other contexts, but there was always the possibility that something about TON 618 pushed them into a regime where new effects might appear. Another subtle aspect of the pre-Webb picture was how TON 618 was used as a benchmark. Because it was so massive and so luminous, it often served as an example in discussions about the upper limits of black hole growth. If models could explain how TON 618 formed, they were considered robust. If not, the models might need revision. In that sense, TON 618 was not just an object of study. It was a test case for broader theories about how structure forms in the universe. Yet despite its importance, much of what was said about it carried a quiet caveat. Phrases like estimated mass and likely structure, and suggests that, appeared frequently in the literature. This was not a sign of weakness. It was a reflection of the reality of working at the edge of observational capability. Science at this scale often advances by narrowing uncertainties rather than eliminating them entirely. There was also an awareness that selection effects might be at play. TON 618 was easy to detect because it was bright. That did not necessarily mean it was the most massive black hole in the universe. It might simply be one of the easiest to observe. There could be others that were just as large or larger, hidden in dustier or less active galaxies, shining less brightly and therefore escaping detection. So even the title of largest known was understood as provisional. All of this set the stage for what James Webb could offer. Not a complete rewrite of the story, but a chance to fill in some of the missing detail. A chance to see through dust rather than around it. A chance to separate different components of the system rather than blending them into a single, overwhelming glow. Before Webb, TON 618 was already a colossus in the data. It was a powerful point of reference for discussions about black hole growth, galaxy evolution, and the early universe. But it was also, in a sense, a silhouette. A massive shape defined by its outline rather than by its internal structure. The anticipation around Webb was built on the hope that this silhouette could be given more depth, that the environment around the black hole could be mapped more clearly, that the relationship between the quasar and its host galaxy could be understood in more detail. What happens when you can see the infrared glow of dust that once blocked your view? What happens when you can measure temperatures, compositions and motions in regions that were previously hidden? When the James Webb Space Telescope finally began its work, it did not arrive with a dramatic countdown aimed at any single object. There was no moment where a switch was flipped and suddenly the universe became clearer all at once. Instead, there was a careful, methodical process. Instruments were tested, mirrors were aligned, temperatures were stabilized. Every system was checked and rechecked, because this telescope was not orbiting close enough for anyone to adjust it by hand. It was parked far beyond the Moon, at a gravitational balance point where Earth and the Sun gently tug in opposite directions, allowing Webb to stay in a stable position while it quietly looks outward. From that distant vantage point, it began to collect a different kind of light than most telescopes before it. Visible light, the kind our eyes see, is only a small slice of the full spectrum of radiation that fills the universe. Infrared light, which has longer wavelengths, carries information about cooler objects and regions hidden behind dust. It is the glow of warmth rather than the shine of brightness. Webb was designed to be especially sensitive to this part of the spectrum, and that design choice shapes everything it observes. For something like TON 618, this makes a profound difference. Before Webb, astronomers were often working around obstacles. Dust in the host galaxy and in the space between galaxies absorbs and scatters visible light. This can dim, distort, or completely hide structures. Quasars, which are already extremely bright, can overwhelm nearby features in images, making it hard to separate what belongs to the black hole's immediate environment and what belongs to the larger galaxy. Infrared light changes that balance. It can pass through dust more easily. It can reveal cooler regions that do not stand out in visible light. It can show the glow of material that has absorbed energy from the quasar and re-emitted it at longer wavelengths. So when Webb began observing distant quasars, including the one powered by TON 618, it was not just taking sharper pictures, it was opening a new window into how these systems are built. The process starts with collecting photons, tiny packets of energy that have travelled across billions of years of expanding space. These photons hit Webb's large, gold-coated mirror and are focused onto its instruments. Each instrument is tuned to analyse different parts of the infrared spectrum, splitting the incoming light into fine slices of wavelength. This is not done for aesthetic reasons. Each slice carries specific information. Certain wavelengths are associated with particular elements and molecules. Others reveal temperature. Some show how fast material is moving toward or away from the telescope. By combining these pieces, astronomers can build a layered understanding of what is happening in regions that cannot be seen directly. In the case of TON 618, one of the first things Webb helped clarify was the structure of the dust and gas around the quasar. Earlier observations hinted at large amounts of dust, but they could not map its distribution in detail. Webb's sensitivity allowed researchers to see where that dust was concentrated, how warm it was, and how it was arranged around the central engine. This matters because dust is not just a passive veil. It plays an active role in how energy moves through a galaxy. When intense radiation from the accretion disk hits dust grains, those grains heat up and then release that energy in the infrared. This can create a kind of glowing halo around the quasar. By measuring the shape and intensity of that infrared glow, astronomers can estimate how far the influence of the black hole's energy extends into the surrounding galaxy. Webb's data suggested that this region was extensive. The quasar's energy was not confined to a small central zone. It was affecting gas and dust across large scales, potentially shaping the conditions for star formation far from the black hole itself. Another area where Webb provided new clarity was in separating different components of the system. The light from a quasar is a mixture of contributions from several sources. There is the hot, inner part of the accretion disk. There are cooler outer parts of the disk. There is dust in a roughly torus-shaped structure around the centre. There is starlight from the host galaxy. In earlier observations, these components often blended together. Webb's spectral resolution allowed astronomers to tease them apart more effectively. By looking at how the brightness changed across different wavelengths, they could identify which parts of the signal came from hot gas close to the black hole and which came from cooler material farther out. This separation is important for refining mass estimates. The motion of gas in the inner regions of the accretion disk is what provides the strongest clue about the black hole's gravitational pull. If light from outer, slower-moving regions is mixed in, it can blur the picture and introduce errors. By isolating the contribution from the innermost regions more cleanly, Webb's data helps tighten the range of possible mass values. It does not eliminate uncertainty, but it narrows it. Another contribution comes from Webb's ability to detect specific molecular signatures in the infrared. Molecules like carbon monoxide and water vapour have characteristic absorption and emission lines in this part of the spectrum. These lines can reveal the presence and movement of cold gas in and around the galaxy. For TON 618, this provides a way to study the raw material for star formation. If large reservoirs of cold gas are present, the galaxy might be actively forming new stars. If that gas is being heated or pushed away by the quasar's energy, star formation might be suppressed. Webb's observations suggest a complex balance. There are signs of significant amounts of gas, but also evidence that powerful radiation and outflows from the central region are influencing how that gas is distributed. This feeds into a broader question about the relationship between supermassive black holes and their host galaxies. For years, astronomers have debated whether black holes primarily respond to the growth of their galaxies, or whether they actively regulate that growth. In nearby galaxies, there is a rough correlation between the mass of the central black hole and the mass of the galaxy's bulge. This suggests some form of coevolution. But in the early universe, and especially for extreme objects like TON 618, that relationship may not hold as neatly. Webb's ability to measure the properties of the host galaxy in the infrared helps address this. By detecting the light from older stars and the glow of dust heated by young stars, astronomers can estimate the galaxy's total mass and its star formation rate more accurately than before. Early results indicate that the black hole in TON 618's galaxy may indeed be unusually massive compared to the galaxy itself. This strengthens the idea that, at least in some cases, black holes can grow faster than their hosts. Another subtle but important contribution from Webb comes from its ability to measure the shape of the quasar's spectrum in fine detail. The spectrum is not just a series of lines and peaks. It has a continuum, a smooth background of light that reflects the overall temperature and structure of the emitting regions. By modelling this continuum, astronomers can estimate how much material is falling into the black hole, and how efficiently that process is converting mass into energy. This efficiency is linked to the black hole's spin and the geometry of the accretion disk. Webb's data allows for more precise modelling of these factors. In the case of TON 618, the quasar appears to be operating near the upper limits of what theory predicts for steady accretion. That suggests a system that has been feeding consistently and effectively for a long time. The telescope also helps in studying the motion of material not just in the disk but in outflows. Many quasars drive winds, streams of gas that are pushed away from the central region by radiation pressure or magnetic forces. These winds can carry significant amounts of mass and energy into the surrounding galaxy. In the infrared, Webb can detect signatures of these outflows in the absorption lines of certain molecules and ions. By measuring how these lines are shifted, astronomers can determine how fast the gas is moving and in which direction. For TON 618, there is evidence of powerful outflows that extend far beyond the immediate vicinity of the black hole. These outflows are another way the quasar can influence the evolution of its host galaxy, potentially clearing out gas that would otherwise form new stars. All of this adds up to a picture that is more detailed but also more complex than what existed before. Rather than a simple model of a massive black hole sitting at the centre of a galaxy and shining brightly, Webb reveals a layered system. There is a central region of extreme gravity and high-speed motion. Around it is a thick, structured disk of gas and dust. Beyond that are regions where radiation and winds interact with the wider galaxy, shaping its future. This complexity is part of what makes the idea of lifting the cosmic curtain feel appropriate. The curtain is not removed in one motion. It is drawn back gradually, revealing one layer at a time. Another aspect of Webb's contribution is its ability to observe similar systems at different stages of cosmic history. By building a sample of distant quasars and studying them in the same way, astronomers can look for trends. Do black holes of a certain size tend to appear at certain times in the universe's history? Do their host galaxies share common features? Does the balance between black hole growth and star formation change over time? TON 618 becomes one point in this larger pattern. It is an extreme point, but it is still part of a broader population. This comparative approach helps put its scale into context. It shows not just how large TON 618 is, but how it fits into the distribution of black hole sizes across the universe. Webb's sensitivity also allows for the detection of fainter companions, small galaxies or streams of material that might be interacting with the main host galaxy. These interactions can provide fuel for the black hole, funneling gas inward through gravitational disturbances. In some systems, Webb has revealed signs of past mergers, where two galaxies collided and combined. These events can dramatically reshape a galaxy and drive bursts of black hole growth. For TON 618, evidence of such interactions would help explain how it acquired so much mass. While the data is still being analysed, the ability to look for these faint features is a new capability that did not exist at this level before. There is also a temporal aspect to Webb's observations that is easy to overlook. Because it's looking so far back in time, each quasar observed is effectively a snapshot of a different era in the universe's development. By comparing TON 618 to other quasars at slightly different redshifts, astronomers can build a timeline of how these systems evolve. This can show, for example, whether the most massive black holes tend to appear earlier or later in cosmic history, and how their growth rates change. This broader view helps turn TON 618 from a standalone curiosity into a data point in a much larger story about how structure forms and changes on the larger scales. All of this, however, still rests on interpretation. Webb provides more detailed and more reliable data, but the step from data to understanding still involves models and assumptions. For example, Converting infrared brightness into a star formation rate requires assumptions about how dust and gas are distributed and how efficiently stars form from that gas. Estimating black hole mass from spectral lines still involves assumptions about the geometry and motion of the accretion disk. What Webb does is reduce the number of unknowns. It allows astronomers to test their assumptions more directly, to check whether a model that works for one wavelength also works for another. This process of cross-checking is one of the quiet strengths of modern astronomy. No single observation stands alone. Each new set of data is compared against existing models, and those models are adjusted or replaced as needed. So when we talk about Webb lifting a curtain, it is not a one-time reveal. It is an ongoing process of refinement. There is something fitting about the way this mirrors the subject itself. TON 618 is not a static object. It is a dynamic system, constantly changing as it feeds, radiates, and interacts with its surroundings. Our understanding of it is also dynamic, changing as new tools and new ideas come into play. As Webb continues to observe, the picture of TON 618 will likely continue to evolve. New features may be identified, measurements may become more precise, theories about how such a massive black hole formed and grew may be adjusted. What remains steady is the sense that this object sits at the far edge of what we can currently study. It is a kind of benchmark, a system that tests the limits of our instruments and our models. There is a quiet satisfaction in that. Not because it means we have reached a final answer, but because it means there is still more to learn. There is a quiet assumption most of us carry without thinking about it, that seeing is the same as knowing. If something is visible, then it is understood. If it is hidden, then it remains a mystery. In everyday life, that idea often works well enough. Turn on a light in a dark room and suddenly the furniture, the walls and the floor fall into place. You can move without bumping into things. You feel oriented. But when it comes to the deep universe, light does not always play the role of a helpful guide. Sometimes it gets in the way, sometimes it hides more than it reveals, and sometimes the most important information is carried not by the light we see, but by the faint warmth and subtle motion that exist beyond the reach of our eyes. This is where the story of TON 618 and the James Webb Space Telescope takes a particularly interesting turn. Before Webb, much of what astronomers knew about distant quasars came from visible and near-infrared light. That light is powerful, especially from something as bright as a quasar, but it is also selective. It tends to highlight the hottest, most energetic regions and wash out the quieter, cooler ones. It also struggles to pass through dust, which is abundant in galaxies, especially those that are actively forming stars or feeding a central black hole. So the picture that emerged was often one of extremes: bright cores, sharp spectral lines, a general sense of mass and distance, but the more subtle features, the slow-moving gas, the cooler dust, the broad faint structures that connect the black hole to the rest of the galaxy, were harder to detect. Infrared observation changes that balance. Heat, even at relatively low temperatures, produces infrared radiation. Dust grains warmed by nearby stars or by the intense energy of a quasar glow in the infrared. Cold gas clouds absorb energy and re-emit it at these longer wavelengths. Motion leaves its mark as well, shifting the wavelengths of specific molecular signatures in ways that can be measured with careful instruments. Webb was built to take advantage of all of this. Instead of relying on the sharp, bright signals of visible light, it listens for the softer, more spread-out hum of infrared radiation. This allows it to trace the presence of material that would otherwise remain hidden behind veils of dust or lost in the glare of a quasar's core. For TON 618, this approach opens up an entirely different view of the system. One of the first things to consider is dust itself. In astronomy, dust is not like the dust that settles on a shelf. It is made of tiny grains of carbon, silicates, and other elements, often smaller than a grain of sand. These grains form in the outer layers of stars and are spread through space when those stars shed material or explode. In a galaxy, dust tends to collect in clouds and lanes, often mixed with gas. It plays a crucial role in star formation by helping gas cool and collapse into new stars, but it also blocks visible light. When you look at a dusty region in visible wavelengths, you often see dark patches or obscured areas where stars and structures are hidden. In the host galaxy of TON 618, dust is abundant. This is not surprising. The early universe was a busy place. Stars were forming at high rates, and galaxies were colliding and merging, stirring up gas and dust and concentrating it in central regions. The quasar itself adds to this complexity. The intense radiation from the accretion disk can heat dust and even destroy it in the very inner regions, while leaving cooler dust farther out intact. So instead of a simple, uniform distribution, the dust around TON 618 is arranged in layers and structures. There is likely a thick, roughly donut-shaped region of dust around the central black hole, often referred to as a torus. Beyond that, there are dust clouds scattered through the wider galaxy. Visible light struggles to penetrate this environment. Infrared light, with its longer wavelengths, passes through more easily. When Webb observes this region, it can detect the glow of dust at different temperatures. Hotter dust near the quasar shines more brightly at shorter infrared wavelengths. Cooler dust farther out emits at longer wavelengths. By measuring the intensity of light across this range, astronomers can build a temperature map of the dust. This temperature map is not just a curiosity. It reveals how energy from the quasar is distributed through the galaxy. If dust far from the centre is warmer than expected, it suggests that the quasar's radiation is reaching and heating those regions. If some areas remain cool, it might indicate shielding by denser dust clouds, or a geometry that blocks the radiation's path. In the case of TON 618, the data suggests that the quasar's influence extends across large regions of the host galaxy. The dust is not just warm near the centre, there are signs of heating at significant distances, implying that energy is being carried outward, either by radiation, by winds, or by a combination of both. This brings us to motion. Motion in space does not announce itself in obvious ways. You do not see arrows pointing in the direction gas is flowing. Instead, you infer motion by looking at how light changes. Certain molecules absorb and emit light at very specific wavelengths. Carbon monoxide, for example, has a set of well-known infrared lines. When a cloud of gas containing carbon monoxide moves toward or away from the observer, those lines shift slightly in wavelength due to the Doppler effect. By measuring these shifts across different parts of a galaxy, astronomers can build a picture of how gas is moving. Is it rotating? Is it falling inward? Is it being pushed outward in a wind? Webb's sensitivity allows it to detect these molecular signatures even in very distant galaxies. For TON 618, this means that researchers can look for evidence of large-scale gas flows associated with the quasar. The presence of outflows is particularly important. A powerful quasar can drive winds that push gas away from the centre of the galaxy. These winds can carry energy and momentum into the surrounding environment, heating gas and sometimes ejecting it entirely from the galaxy's gravitational pull. If enough gas is removed or heated, star formation can slow down or stop. In this way, the black hole can indirectly regulate the growth of its host galaxy. Infrared observations provide one of the best ways to detect these outflows in dusty, distant systems. The gas in these winds can be traced by shifted absorption and emission lines. The width of these lines can also indicate how turbulent or fast-moving the gas is. For TON 618, Webb's data points to complex motion in the surrounding gas. There are signs of both rotation and outward flow. This suggests a dynamic environment where material is not just falling into the black hole, but also being pushed back out into the galaxy. This back and forth exchange of matter and energy is part of what makes the system so interesting. It is not a one-way street where everything simply disappears into the black hole. It is a continuous interaction, with feedback loops that connect the smallest scales near the event horizon to the larger scales of the galaxy. Heat plays a role here as well. Gas near the black hole is heated to extreme temperatures by friction and compression as it spirals inward. This hot gas emits radiation that can heat surrounding material. Some of that energy can also be transferred mechanically through winds and jets. By mapping the temperature of gas and dust at different distances from the centre, astronomers can infer how energy flows through the system. Webb's ability to detect faint infrared emission from cooler regions makes it possible to see this energy gradient. You can trace a path from the blazing inner disk, through warmer dust in the torus, out to cooler dust and gas in the wider galaxy. This layered structure is a key part of understanding the true scale of TON 618's influence. The black hole itself may occupy a relatively small region, but the effects of its activity spread across a much larger volume of space. Another subtle aspect of seeing where light fails is the ability to study regions that are completely hidden in visible wavelengths. There can be dense clumps of dust and gas that block almost all optical light. In visible images, these appear as dark patches or are simply invisible. In the infrared, these same regions can glow softly, revealing their presence and shape. For the host galaxy of TON 618, this means that Webb can provide a more complete census of its structure. Features that were previously guessed at can now be observed directly. This helps refine estimates of the galaxy's mass and size. It also helps in mapping the distribution of star-forming regions. Young stars are often born in dusty environments. Their light is absorbed by dust and re-emitted in the infrared. By detecting this re-emitted light, Webb can identify areas of active star formation that might otherwise be missed. This is particularly relevant for understanding how the black hole and the galaxy interact. If star formation is happening in some regions but not others, it can hint at where the quasar's influence is strongest. For example, if regions close to the centre show little sign of star formation while outer regions remain active, it suggests that the black hole's energy is suppressing star formation nearby, but not farther out. This kind of spatial pattern is hard to detect without infrared data. Another layer of information comes from the way dust grains themselves respond to their environment. The composition and size of dust grains can change depending on temperature, radiation, and the history of star formation in a region. Different types of dust emit infrared light in slightly different ways. By analysing the shape of the infrared spectrum, astronomers can infer what kinds of dust are present. For TON 618, this can provide clues about the chemical enrichment of the galaxy. Heavy elements are produced in stars and spread through space when those stars die. The presence of certain dust features suggests that multiple generations of stars have already lived and died in this system, enriching the environment with complex materials. This adds another temporal dimension to the picture. Not only are we seeing TON 618 as it was billions of years ago, but we're also seeing evidence of an even earlier history of star formation within its galaxy. Motion, heat, and dust together create a kind of three-dimensional map of the system. Motion tells you how material is moving, heat tells you where energy is being deposited, dust tells you where material is concentrated and how light and energy are being filtered. Webb's role is to gather these signals with enough precision and sensitivity that they can be combined into a coherent picture. This is not a simple process. Each measurement comes with uncertainties. Spectral lines can overlap. Dust emission can be confused with starlight. Motion along the line of sight can be mixed with motion in the plane of the sky. So astronomers use models to interpret the data. They simulate how gas and dust should behave in different scenarios and compare those simulations to what Webb observes. When a model matches the data well, it becomes a candidate explanation for what is happening in the real system. This process of modelling and comparison is ongoing. It is part of what makes the picture of TON 618 evolve over time rather than settle into a final form. There is something quietly fitting about the idea that to understand a black hole, an object defined by darkness, we rely so heavily on heat. Not the blinding heat of a star's surface, but the subtle warmth of dust grains and gas clouds, glowing just enough in the infrared to tell their story. It is a reminder that in the universe, absence and presence are often intertwined. The black hole itself is invisible, but its presence is written into the temperature of dust, the motion of gas, and the structure of an entire galaxy. As you let this settle in, you might notice how different this way of seeing is from everyday experience. We're used to sharp outlines, clear edges, and direct views. The universe, especially at this scale and distance, offers something softer and more layered. Signals overlap, structures blur. Meaning is extracted through careful analysis rather than immediate recognition. This does not make the picture less real. It simply makes it more subtle. Looking at TON 618 through Webb's infrared eyes is like listening to a distant city at night. You do not see individual people or buildings clearly. You hear a low, continuous hum, punctuated by occasional sharper sounds. From that you infer the presence of streets, movement, and activity. In the same way, astronomers listen to the hum of infrared radiation from dust and gas, and infer the presence of flows, structures, and interactions on a scale that cannot be directly imaged in detail. This listening, rather than seeing, is part of what makes the process feel different. It is a slower, more interpretive way of engaging with the data. As Webb continues to observe TON 618 and similar systems, this map of heat, dust, and motion will become more detailed. New features may be identified. The shapes of outflows may be traced more clearly. The distribution of star-forming regions may be refined. Each of these additions helps build a more complete sense of how this enormous black hole fits into the life of its galaxy. And as that picture grows, the idea of scale takes on a new form. It is not just about how large the black hole is in terms of mass or size. It is about how far its influence reaches, how deeply it reshapes its surroundings, and how many layers of interaction connect its central gravity to the broader structure of the galaxy and beyond. Somewhere between the idea of a simple circle and the reality of a constantly shifting storm, the accretion disk around TON 618 takes shape. Calling it a disk is useful, but it can also be misleading. The word suggests something flat, calm, and neatly arranged, like a vinyl record or the surface of a quiet lake. What actually exists around this black hole is closer to a vast three-dimensional region of motion, heat, and pressure, where matter does not settle so much as it negotiates, moment by moment, with gravity. To understand why this structure defies intuition, it helps to start with something familiar. Imagine water swirling down a drain. Far from the centre, the motion is slow and gentle. You can see leaves or small bits of debris drifting along wide, lazy curves. As you move close to the drain, the water speeds up. The paths tighten. The motion becomes more focused and more forceful. At the very centre, everything disappears into a narrow opening. This analogy works only up to a point. Around TON 618, there is no solid surface beneath the flow, no simple hole at the centre. There is instead a region of space where gravity becomes so strong that the usual rules of motion change, and the material involved is not water, but gas and dust heated to temperatures that can strip atoms apart and turn matter into a glowing plasma. The accretion disk begins far from the event horizon, in regions where gas from the host galaxy starts to feel the pull of the black hole more strongly than the pull of the surrounding stars and dark matter. This gas does not fall straight in. It almost never does. Instead, it carries angular momentum, a kind of built-in sideways motion. Because of that, it begins to orbit. As more gas arrives, these orbits begin to flatten into a broad, rotating structure. Collisions between particles and interactions between different streams of gas cause energy to be lost as heat. That loss of energy allows the material to slowly spiral inward, moving from larger orbits to smaller ones over time. In a system like TON 618, this process is happening on an enormous scale. The outer regions of the disk can be light years across. That means the distance from the far edge of the disk to the centre is comparable to the distance between stars in our own galaxy. Within this vast structure, conditions vary dramatically. Far from the black hole, the gas is relatively cool by cosmic standards. It may be only a few hundred or a few thousand degrees. Dust grains can survive here, mixed in with the gas. These regions glow primarily in the infrared. As material moves inward, it speeds up. The gravitational pull becomes stronger. Friction and compression heat the gas to tens of thousands, then millions of degrees. Dust grains are destroyed. Atoms are stripped of their electrons. The gas becomes a plasma, emitting light across a wide range of wavelengths, including visible light and even X-rays. This gradual change in conditions creates a layered structure, not in neat, uniform bands, but in overlapping zones that shift and ripple as the flow of material changes. One of the reasons this is hard to picture is that nothing in everyday experience behaves quite like this. We're used to thinking of disks as solid, or at least stable, a spinning top, a wheel, a record. They rotate, but they keep their shape. An accretion disk is not a solid object. It is more like a crowd of individual particles, each following its own path, interacting with neighbours through collisions, magnetic fields, and pressure. The overall shape emerges from these countless small interactions rather than from any rigid structure. Magnetic fields play a surprisingly important role here. The gas in the disk is often ionized, which means it carries electric charges. Moving charge particles create and respond to magnetic fields. These fields can tangle, stretch, and reconnect, transferring energy and momentum through the disk. This magnetic activity is one of the main drivers of what is called viscosity in the disk. In everyday terms, viscosity is a measure of how thick or resistant to flow a fluid is. Honey is more viscous than water. In an accretion disk, viscosity is not caused by the stickiness of the gas, but by turbulent motions and magnetic interactions that allow angular momentum to be transferred outward. This outward transfer of angular momentum is what allows material to move inward. Gas in the inner parts of the disk gives up some of its angular momentum to gas farther out, slowing down and spiralling closer to the black hole. The outer gas, in turn, speeds up and moves outward slightly. So the disk is not just a one-way flow toward the centre. It is a complex, two-way exchange of energy and momentum across its entire structure. In a system as massive as TON 618, these processes operate on scales and energies that push the limits of current models. The disk is so large and so luminous that small changes in the rate of inflow can have dramatic effects on the amount of energy released. This brings us to one of the most counterintuitive aspects of accretion disks. They are not just a way for matter to fall into a black hole. They are also one of the most efficient energy-producing systems in the universe. When matter falls into a gravitational well, it loses potential energy. That energy has to go somewhere. In an accretion disk, much of it is converted into heat and radiation before the material ever crosses the event horizon. For TON 618, the amount of energy released in this process is staggering. The quasar powered by this disk can outshine entire galaxies, and yet the black hole itself remains dark. The light we see is the last signal sent by matter before it disappears. This creates a strange inversion of expectations. The brightest part of the system is not the central object, it is the swirling, doomed material around it. Another layer of complexity comes from the fact that the disk is not necessarily aligned in a simple way with the rest of the galaxy. The gas that feeds the disk can arrive from different directions, especially if the host galaxy has experienced mergers or interactions with other galaxies. This can lead to warps and twists in the disk. Different regions can be tilted at slightly different angles. Over time, gravitational and magnetic forces tend to smooth these differences out, but the process can be slow and uneven. In observations of distant quasars, there are hints of such warped structures. The light we receive can show signatures that suggest the disk is not a perfectly flat, symmetrical shape. For TON 618, This means the disk is likely a dynamic, evolving structure rather than a static one. Its shape and orientation may change over time as new material flows in and as the black hole's own spin influences the surrounding space. Speaking of spin, this is another factor that defies simple intuition. Black holes can rotate. In fact, many are thought to spin very rapidly, carrying enormous amounts of angular momentum. A spinning black hole drags space itself around with it, an effect known as frame dragging. This means that the paths available to matter in the accretion disk are altered. Orbits can become more stable closer to the event horizon if the disk rotates in the same direction as the black hole's spin. If it rotates in the opposite direction, the stable region is pushed farther out. For a black hole as massive as TON 618, this effect operates on a huge scale. The inner edge of the disk, the point where stable orbits end and material plunges inward, depends on the black hole's spin. This, in turn, affects how much energy can be extracted from the infalling matter. If the black hole is spinning rapidly and the disk is aligned with that spin, the system can be especially efficient at converting mass into radiation. This could help explain the extreme brightness of TON 618's quasar. But measuring spin at such a distance is difficult. It relies on subtle features in the spectrum of the emitted light and on models of how the inner disk behaves. Webb's data can help refine these models, but the picture remains one of probabilities and ranges rather than precise values. Another intuitive hurdle is the thickness of the disk. In simple drawings, accretion disks are often shown as thin, flat rings. In reality, especially for very luminous quasars, the disk can be quite thick. Radiation pressure from the intense light emitted in the inner regions can puff up the disk, making it more like a thick, glowing torus than a thin sheet. This thickness affects how light escapes the system. Some directions may be relatively clear, allowing us to see the bright inner regions directly. Other directions may be blocked by dust and gas, forcing the light to scatter or be absorbed and re-emitted before it reaches us. This is one of the reasons why quasars can look different depending on the angle from which they are observed. The same basic system can appear as a bright, unobscured quasar or as a more hidden, dust-enshrouded active galaxy. For TON 618, the fact that we see it as an extremely bright quasar suggests that our line of sight is relatively clear. We are likely looking down a path that is not heavily blocked by the thickest parts of the disk and surrounding dust. This geometry is another piece of the puzzle when it comes to interpreting the data. The light we receive is shaped not just by the physical conditions in the disk, but by the angle at which we happen to be viewing the system. One of the more subtle and fascinating features of accretion disks is their variability. The flow of gas into the black hole is not perfectly steady. It can change over time due to fluctuations in the supply of material, instabilities within the disk, or interactions with other structures in the galaxy. These changes can lead to variations in the brightness of the quasar. For TON 618, these variations are relatively slow and subtle, partly because of the system's immense size. Changes in the outer regions of the disk can take years or even decades, as seen from Earth, to propagate inward. This slow pace can make the system feel almost static on human timescales, even though, in absolute terms, it is a place of constant, intense activity. Another intuitive challenge comes from the idea of boundaries. We tend to think of a disk as having a clear inner and outer edge. In reality, these boundaries are fuzzy. The outer edge of the disk is where the gas transitions from being part of the general galactic environment to being part of the black hole's immediate domain. This transition is gradual and influenced by the galaxy's overall gravitational field, the distribution of gas, and the presence of other structures like stars and dark matter. The inner edge, near the event horizon, is also not a sharp line in a physical sense. It is defined by the last stable orbits allowed by the black hole's gravity and spin. Inside that region, material plunges inward rapidly. But even here, the transition is not like crossing a painted line on the ground. It is a region where the nature of motion changes. Thinking about these fuzzy boundaries can make the disk feel less like an object and more like a process. It is not something you could point to and say, here it begins and here it ends. It is something that emerges from the continuous interaction between gravity, motion and energy. This process-oriented view is another reason the disk defies simple mental pictures. We are more comfortable with things than with flows. There is also a scale mismatch that can be hard to reconcile. On the smallest scales, near the event horizon, conditions are extreme. Space and time are strongly curved. Matter moves at a significant fraction of the speed of light. On the larger scales, in the outer disk and the surrounding galaxy, conditions are more familiar. Gas clouds drift. Stars form and die. Gravity still matters, but it operates in ways that fit more easily into everyday intuition. The disk connects these two regimes. It is a bridge between the relativistic and the classical, the extreme and the ordinary. This bridging role makes it especially interesting scientifically, because it is one of the few places where we can study how these different physical domains interact. For TON 618, this bridge is longer and more massive than in almost any other known system. That makes it a valuable laboratory for testing theories about accretion, magnetism, radiation, and gravity. And yet, for all its scientific importance, the disk remains something we cannot directly see in detail. Even with Webb's capabilities, we are still working with indirect signals, integrated over vast distances and complex structures. The images and spectra we obtain are like long exposure photographs of a city at night, taken from very far away. You can see the glow of lights, the general layout of streets, the brighter clusters of activity, but you cannot see individual people or cars. This distance from the details is part of what keeps the disk in the realm of the abstract. We know it is there. We can describe its properties. We can model its behaviour, but we cannot experience it in any direct way. As you think about this, there is a quiet contrast between the simplicity of the word disk and the richness of what it actually represents. It is not a shape so much as a system, a place where gravity, motion, heat and magnetism are in constant conversation. And in the case of TON 618, that conversation is taking place on a scale that stretches across light years and over time scales that reach back into the early history of the universe. How do you talk about distances, masses and energies when they no longer fit comfortably into familiar categories? There comes a moment, usually quietly, when a number stops behaving like a number and starts behaving like a symbol. It still has digits. It can still be written down, compared, placed into an equation. But somewhere along the way, it slips free from the part of the mind that connects quantities to experience. It becomes something you recognize rather than something you feel. This happens to most of us with words like million or billion. We learn their definitions in school. We know intellectually what they represent. But if you were asked to imagine a million of anything, a million grains of sand, a million seconds, a million steps, the image quickly dissolves into a vague sense of a lot. With TON 618, this effect is not just present, it is unavoidable. When astronomers say this black hole has a mass of around 66 billion suns, they are offering a precise figure based on careful measurement and modelling. That number is meaningful within the language of physics. It tells you how strong the gravity is. It tells you how fast gas must move to stay in orbit. It tells you how much energy can be released as matter falls inward. But for the human imagination, 66 billion suns does not land in the same way that a mountain or an ocean does. There is no built-in mental picture for that scale. One of the reasons numbers start to lose their grip at this level is that we rarely encounter large quantities in a continuous way. Most of our counting is done in small sets. We count steps, minutes, people in a room, pages in a book. Even when we deal with larger numbers like money or population, we often interact with them through summaries and symbols rather than direct experience. You do not feel a city of 1,000,000 people as 1,000,000 individual lives. You feel it as a general sense of crowds, buildings and movement. The number becomes a label rather than a collection. With TON 618, the gap between the label and any possible experience is much wider. Let's take time as an example because it is something everyone interacts with every day. A second is familiar. You can count it. A minute is just 60 of those. An hour is manageable. A day has a rhythm you know well. A year is already a stretch. You remember seasons, holidays, changes. 10 years feels like a distinct chapter of life. 100 years pushes beyond most personal memory. It becomes historical. Now consider 1,000,000 years. That is long enough for entire species to rise and disappear. 1,000,000,000 years is long enough for continents to shift, oceans to open and close, and the sun itself to change noticeably in brightness. TON 618 is so far away that the light we see from it today has been travelling for over 10 billion years. That means when that light left, the Earth was not yet a finished planet. Life, if it existed at all, was limited to simple forms in the oceans. This time scale is part of what makes the numbers around TON 618 feel unreal. They do not just exceed personal experience, they exceed the experience of humanity as a whole. Distance works in a similar way. A metre is a step, a kilometre is a walk or a drive. 1,000 kilometres is a journey across a country. 1,000,000 kilometres is already a space scale. It is the distance to the moon and back, more than twice. 1,000,000,000 kilometres takes you beyond the orbit of Saturn. A light year, nearly 10 trillion kilometres, is a distance so large that it only really makes sense in terms of how long light takes to cross it, rather than how far it is in space. Now multiply that by billions. TON 618 is not just far, it is far in a way that makes the idea of travel meaningless. There is no practical sense in which you could imagine going there, even in thought. It exists at a remove that is more like a different layer of reality than a different location. Mass, time, distance, energy. All of these numbers pile up around TON 618 until they form a kind of wall. Not a wall that blocks understanding, but one that changes the way understanding has to work. At this point, comparison becomes one of the few tools left. Astronomers often compare the mass of black holes to the mass of the Sun because the Sun is a familiar reference point. It is something you see in the sky. It warms your planet. It defines your day. But even that comparison starts to break down when the multiplier reaches into the tens of billions. You can say this black hole is as massive as 66 billion suns, but that does not give you a sense of weight or presence. It gives you a sense of repetition. The Sun, over and over again, in a stack so tall you cannot see the top. Sometimes people try to bring these numbers closer by converting them into everyday terms. For example, you might hear that the event horizon of TON 618 is so large that it could swallow the entire solar system and still have room to spare. This helps a little. It ties the black hole's size to something you have a mental map of. You know where the planets are roughly. You can imagine their orbits. But even here the comparison has limits. The solar system itself is mostly empty space. The distances between planets are vast. Saying something could swallow it whole still leaves a lot of room for interpretation. Another common technique is to use time-based analogies. For example, if you count one number per second, it would take you about 31 years to reach 1 billion. To count to 66 billion at that rate would take more than 2,000 years. This kind of comparison can make the scale feel more grounded. It connects the number to a human activity, counting, and a human time frame, a lifetime or several lifetimes. But even then, the connection is indirect. You're not experiencing the number. You're experiencing the idea of a very long task. The reason these techniques struggle is that our brains are not built to represent large quantities as continuous experiences. We rely on categories: small, medium, large, very large. Beyond that, things tend to collapse into a single mental box labelled huge. TON 618 lives firmly in that last box. There is also a subtle emotional component to this. Numbers at this scale can feel oddly neutral. A mountain can feel imposing, an ocean can feel vast and powerful, a storm can feel threatening. But 66 billion does not carry a built-in emotional tone. It is impressive, but in a detached way. It does not trigger the same kind of physical response. This is part of why scientific images and narratives often focus on visual or dynamic aspects rather than raw numbers. A picture of a swirling galaxy or a glowing quasar can evoke a sense of motion and energy that a list of measurements cannot. Webb's observations of TON 618 help in this regard. They add texture to the numbers. Instead of just knowing that the black hole is massive, you can see how its energy spreads through dust, how its gravity shapes the motion of gas, how its presence defines the structure of a galaxy. These patterns are something the mind can engage with more easily than a string of digits. Another reason numbers start to feel unreal in this context is that they often represent averages or estimates rather than direct measurements. When astronomers say TON 618 has a mass of about 66 billion suns, that figure comes with an uncertainty. It might be somewhat more, it might be somewhat less. The exact number depends on models of how gas moves, how light is emitted, and how the geometry of the system is arranged. These models are grounded in physics, but they are still simplifications of a complex reality. So the number is not a single, fixed truth. It is a best estimate within a range. This can make it feel even more abstract. You're not just dealing with a large number. You're dealing with a large number that could shift as understanding improves. The same is true for distances, temperatures and energies. Each value is a marker in a landscape of possibility rather than a final point. There is a kind of quiet honesty in this. It reflects the way science actually works. Knowledge is not a set of perfect answers. It is a process of narrowing down what is likely. TON 618 sits at the far end of that process. It is so distant and so extreme that every measurement pushes the limits of what instruments and models can do. This does not make the numbers meaningless. It makes them part of an ongoing conversation. Another aspect of scale that can make numbers feel unreal is the way different quantities interact. For example, consider the energy output of TON 618's quasar. It can be on the order of trillions of times the luminosity of the Sun. That number alone is hard to grasp. But what does it mean in practical terms? It means that, for the period of time we're observing, the system is converting mass into energy at a rate that dwarfs most other processes in the universe. It means that a small fraction of the mass falling into the black hole is being turned into radiation with extraordinary efficiency. In fact, accretion onto a black hole can be more efficient at producing energy than nuclear fusion, the process that powers stars. Fusion converts about 0.7% of mass into energy. Accretion can convert several percent, and in some configurations even more. So when you look at TON 618's brightness, you are seeing a process that is, in a sense, one of the most efficient engines known. This efficiency is another number that can feel abstract. Percentages and fractions are familiar in everyday contexts, like cooking or budgeting. But when the base quantity is tens of billions of suns, even a small percentage represents an enormous amount of mass and energy. It is here that the mind often resorts to generalities. A lot of energy, an immense output, a powerful source. These phrases are not wrong. They are just placeholders for something that resists more precise emotional or sensory representation. Another way to think about this is in terms of density. The average density of a black hole like TON 618, if you spread its mass evenly across the volume defined by its event horizon, can be surprisingly low. In fact, for very massive black holes, the average density can be less than that of water. This is one of those facts that often catches people off guard. A black hole is associated with extreme density, but that density is concentrated at the centre. The region inside the event horizon can be vast. So here you have a system that is both extremely dense at its core and relatively low density when averaged over its full size. This duality can make the numbers feel even stranger. How can something be both heavier than tens of billions of suns and in some sense less dense than a lake? The answer lies in the way gravity works and how mass is distributed, but the emotional impact of the numbers can still feel slippery. There's also the question of how these numbers relate to each other. Mass, distance, time, energy, temperature. In everyday life, these are separate categories. A person can be tall, but not heavy. A day can be long, but not hot. In astrophysics, these quantities are often deeply linked. The mass of a black hole affects the temperature of its accretion disk. The distance to an object affects how bright it appears. The time since the light was emitted affects how its spectrum is shifted. So when you change one number, the others shift as well. This interdependence can make it hard to isolate any single value and treat it as a standalone fact. TON 618 is not just a big mass at a big distance shining with big energy. It is a system where all of these bigs are tied together by the same underlying physics. Another subtle reason numbers start to feel unreal is that they often hide variation. When you hear a single value for the mass or luminosity of TON 618, it is usually an average over time or over different regions. In reality, the system is not uniform. Different parts of the accretion disk have different temperatures. Different streams of gas move at different speeds. The brightness can fluctuate. So the number you hear is a summary, not a snapshot. This is true in many areas of science, but at this scale, the gap between the summary and the underlying complexity can be especially wide. There is also a cultural element to how we respond to large numbers. In everyday language, billion is often used loosely to mean a lot. I've told you 1 billion times. There are 1 billion things to do. This casual use can strip the word of its precision and weight. When you then encounter a scientific statement that uses billion in a literal measured sense, it can be hard to switch back into a more exact mode of thinking. So when you hear 66 billion suns, part of your brain might file it under very many rather than a specific calculated quantity. This is not a failure of understanding. It is a reflection of how language and culture shape perception. Scientists are aware of this gap, which is why they often use multiple ways of describing the same scale. They provide numbers, but they also provide comparisons, visualizations, and stories. The goal is not just to inform, but to help the listener build some kind of mental framework, even if that framework is approximate. With TON 618, that framework might look like this. Imagine a region of space where the central object outweighs most of what surrounds it, where gas moves so fast and gets so hot that it glows across the universe, where the influence of a single gravitational source can shape an entire galaxy. This is not a precise picture, but it is a functional one. There is a quiet acceptance that comes with working at this scale. You do not expect to fully get it in a visceral way. You accept that understanding will be partial, mediated by models and metaphors. This acceptance can actually be a relief. It takes the pressure off. You do not have to force your mind to hold all the numbers at once. You can let them sit in the background as markers, while you focus on the patterns and relationships they describe. In a way, this mirrors how scientists themselves work. They rely on equations and data, but they also rely on intuition about how systems behave. They look for trends, correlations, and anomalies rather than memorizing individual values. TON 618 becomes interesting not just because it is 66 billion of something, but because it sits at the edge of known distributions. It challenges models of growth. It tests ideas about how black holes and galaxies evolve together. So the numbers become part of a story rather than the story itself. There is also a deeper, quieter effect of encountering numbers like these. They can shift perspective. When you spend time thinking about billions of years and billions of suns, the scale of everyday concerns can change, even if only slightly. A missed bus or a delayed email starts to feel like a very local event in a very large universe. This is not about minimizing human experience. It is about placing it within a broader context. TON 618 is a reminder that the universe operates on scales that are far beyond our own, and yet, through careful observation and thought, we can still reach out and learn something about them. How does TON 618 stack up against other massive black holes? What does it look like when placed alongside the biggest objects we know? There is a quiet satisfaction in lining things up side by side. It is one of the oldest ways humans have made sense of the world. This stone is heavier than that one. This tree is taller than the one beside it. This river is wider than the stream that feeds into it. Comparison turns abstract ideas into relationships. It gives shape to scale. When it comes to TON 618, comparison is almost a necessity, because on its own, it floats in a realm of numbers and distances that feel detached from everyday experience. Putting it next to other black holes, other galaxies, and other cosmic structures gives the mind something to hold on to. It turns enormous into a kind of map. A natural place to start is close to home. At the centre of the Milky Way is a black hole known as Sagittarius, a star. It has been studied in detail for decades. Astronomers have tracked the orbits of stars whipping around it, watched gas clouds stretch and tear under its gravity, and even produced an image of its shadow using a network of radio telescopes spread across the Earth. Sagittarius A star has a mass of about 4 million times that of the Sun. That number is already impressive. 4 million suns packed into a region of space smaller than the orbit of Mercury. It shapes the motion of stars in the galactic centre and anchors the structure of the Milky Way in subtle but real ways. Now place TON 618 next to that. TON 618 outweighs Sagittarius A star by a factor of more than 10,000. If Sagittarius A star were the mass of a single coin, TON 618 would be the mass of a small truck. Not just bigger, but in a completely different category of presence. This difference shows up not only in mass, but in influence. Sagittarius A star affects the orbits of stars within a few light years. Beyond that, the combined gravity of the galaxy's stars and dark matter takes over. TON 618, by contrast, sits at the centre of a quasar whose energy output can shape conditions across an entire galaxy. The region over which it can heat, push, and disturb gas is far larger. This comparison alone starts to shift perspective. The black hole we consider supermassive in our own galaxy turns out to be, in cosmic terms, more like a middleweight. Another useful point of reference is the black hole at the centre of the galaxy M87, often called M87 star. This is the one that produced the first direct image of a black hole's shadow in 2019. That image, a glowing ring surrounding a dark centre, became one of the most recognisable scientific pictures of recent years. M87 star has a mass of about 6.5 billion suns. That makes it more than 1,000 times heavier than Sagittarius A star, and places it firmly in the upper tier of known black holes. Its event horizon is so large that light takes days to cross it. For a while, M87 star was one of the main benchmarks for extreme when it came to black hole size. Now place TON 618 next to M87 star. TON 618 is still about 10 times more massive, so even when compared to one of the largest and most famous black holes we have imaged directly, TON 618 stands above it in terms of sheer mass. This begins to outline a kind of hierarchy. There are stellar mass black holes, formed from collapsing stars. There are supermassive black holes, millions or billions of times the mass of the Sun, found in the centres of galaxies. And then there are the few that sit at the very top of that range, sometimes called ultramassive black holes. TON 618 belongs to that last rare category. Another name that often appears in the same conversations is Holmberg 15A's central black hole. Estimates for its mass reach into the tens of billions of suns as well, placing it in a similar class. There are also other distant quasars with black holes that approach this range, so TON 618 is not entirely alone. But the list of objects that can be placed alongside it is short. This scarcity is part of what makes it so useful for comparison. It sits at the extreme end of a distribution, where the rules that seem to apply in the middle of the range might start to bend. For example, in many nearby galaxies, there is a relationship between the mass of the central black hole and the mass of the galaxy's bulge, the dense central region of stars. Roughly speaking, bigger bulges tend to host bigger black holes. This relationship is not exact, but it has been observed often enough to suggest a connection between the growth of black holes and the growth of galaxies. When astronomers try to place TON 618 on this kind of graph, it does not always fit neatly. Its black hole appears to be disproportionately large compared to what is inferred about its host galaxy. This does not mean the relationship is wrong. It might mean that the host galaxy is more massive than we currently think, perhaps hidden by dust or distance. Or it might mean that, in the early universe, black holes could sometimes outpace their galaxies in growth. Comparing TON 618 to more typical systems highlights this tension. Another way to compare is by looking at the size of event horizons. The event horizon of Sagittarius A star is about 24 million kilometers across. That is large enough to swallow the Sun many times over, but small enough that it would fit comfortably inside the orbit of Mercury. The event horizon of M87 star is much larger. It is roughly the size of our entire solar system, extending beyond the orbit of Pluto. For TON 618, the event horizon is estimated to be even larger, potentially several times the diameter of our solar system. So if you imagine lining up these black holes not by mass but by the sheer size of the region, where nothing can escape, you get a sense of how dramatically the scale increases at the top end. Another useful comparison is with galaxies themselves. A typical large galaxy, like the Milky Way, is about 100,000 light-years across. That is the diameter of the region containing most of its stars. The event horizon of TON 618 is tiny compared to that. It is still measured in light hours or light days, not light years. So even the largest black holes do not come close to matching the physical size of their host galaxies. This is an important point because it highlights a subtlety in how we think about influence versus size. TON 618 is not large in the sense of taking up a huge fraction of its galaxy's volume. It is large in the sense of having an outsized effect on its surroundings through gravity and energy output. This distinction becomes clearer when you compare black holes to other massive cosmic structures. Take galaxy clusters, for example. These are collections of hundreds or even thousands of galaxies bound together by gravity. They can span millions of light-years. Their total mass, including dark matter, gas and stars, can reach into the range of 1,000,000 billion suns. Compared to that, even TON 618 is small. So in the grand hierarchy of the universe, black holes, even the largest ones, are not the biggest structures by volume or total mass. They are extreme in density and in the way they concentrate mass into a small region. This brings up an interesting contrast. TON 618 is one of the most massive single objects known, but it is embedded within structures that are, in a different sense, even more massive and more extensive. Another point of comparison comes from looking at the luminosity of the quasar. The quasar powered by TON 618 can shine with the brightness of trillions of suns. This puts it among the most luminous persistent objects in the universe. Compare that to a typical star. Even a very bright star like a blue supergiant might shine with the luminosity of a few million suns. That is impressive, but it is still many orders of magnitude below what a quasar can produce. Even entire galaxies often do not match the output of a powerful quasar. A galaxy like the Milky Way, with hundreds of billions of stars, has a total luminosity that can be comparable to that of a single, extremely bright quasar. So in terms of energy output, TON 618's quasar can rival or exceed entire galaxies. This is another way it stands out in comparison. It is not just a heavy object, it is an energetic one. Looking at timescales provides another layer of contrast. Stars live for millions to billions of years, depending on their mass. Galaxies evolve over billions of years. Galaxy clusters change over even longer periods. the activity of a quasar can be relatively brief on cosmic timescales. A black hole might shine as a quasar for a few 100 million years before its fuel supply dwindles or its environment changes. TON 618, as we see it, is in an active phase. But that phase is just one chapter in a much longer story. Comparing this to the lifespan of a star or a galaxy helps highlight the dynamic nature of black hole growth. They are not always in the same state. They go through periods of feeding and relative quiet. Another interesting comparison is with theoretical limits. There are models that suggest there might be an upper bound to how massive a black hole can grow through normal processes of accretion and mergers. This is not a hard, universal limit, but a kind of practical ceiling based on the availability of material and the way energy feedback can slow growth. TON 618 sits near where some of these models start to strain. It is not clear whether it is close to an absolute maximum or just one of the first examples we have found near the top of a much larger range. Comparing it to simulations of galaxy and black hole formation can highlight where our theories match observations and where they might need adjustment. There is also a comparison to be made with black holes in the early universe. Astronomers have discovered quasars at very high redshifts, meaning they existed when the universe was less than 1 billion years old. Some of these quasars are powered by black holes, with masses of 1 billion suns or more. This raises a question. How did black holes grow so large so quickly? TON 618, seen as it was more than 10 billion years ago, is part of this same general puzzle. It represents a later stage, but still early enough that growth had to be efficient and sustained. By comparing TON 618 to even earlier quasars, astronomers can trace a rough timeline of how black hole mass increases over cosmic history. This kind of comparison turns TON 618 into a milestone. It is a marker along a path of growth rather than an isolated oddity. Another perspective comes from comparing the black hole to the amount of matter in its surrounding galaxy. In many nearby galaxies, the mass of the central black hole is about 0.1% of the mass of the galaxy's bulge. This is a rough rule of thumb, not a strict law. If TON 618 followed this same pattern, its host galaxy would have to be extraordinarily massive, far larger than what is currently inferred from observations. This mismatch suggests either that the galaxy is indeed much more massive than we think, perhaps hidden by dust and distance, or that the relationship between black hole mass and galaxy mass was different in the early universe. Comparing TON 618 to galaxies that follow the normal relationship helps highlight this discrepancy. Another way to think about comparison is to look at physical density. A stellar mass black hole might have an average density far greater than that of atomic nuclei. A supermassive black hole, by contrast, can have an average density lower than that of air. TON 618, being so massive, falls into this latter category. Its event horizon encloses such a large volume that, if you spread its mass evenly across that volume, the result is not especially dense. So in terms of density, TON 618 is not extreme in the same way a small black hole is. This is a counterintuitive comparison. It shows that big does not always mean dense in the way we might expect. Another comparison that can be useful is with dark matter. The total amount of dark matter in a galaxy or galaxy cluster far exceeds the mass of the central black hole. Dark matter does not emit light and interacts very weakly with ordinary matter, but its gravitational influence shapes the structure of galaxies and clusters. So even though TON 618 is one of the most massive known single objects, it is still a small part of the overall mass budget of its cosmic environment. This highlights a broader point. Black holes are dramatic, but they are not the dominant form of mass in the universe. They are more like intense focal points in a much larger gravitational landscape. Comparing TON 618 to the cosmic web itself pushes this idea even further. The cosmic web is the large-scale structure of the universe, a network of filaments made of dark matter and gas, with galaxies and clusters forming at the intersections. This structure spans billions of light-years. TON 618 is a tiny point within this web, so when we compare across the full range of cosmic structures, from planets to stars to black holes to galaxies to clusters to the cosmic web. TON 618 occupies a very specific niche. It is an extreme example of mass concentration, not an extreme example of spatial extent. This layered comparison can help make sense of the different kinds of bigness that exist in the universe. There is also a comparison to be made in terms of observation. Sagittarius A star and M87 star are close enough in cosmic terms that we can observe their immediate environments in detail. We can track individual stars, map the shape of the accretion flow, and even image the shadow of the event horizon. TON 618 is far beyond that range. It appears as a bright point with spectral features, not as a resolved structure. So in terms of how directly we can study it, TON 618 is more distant and more abstract than some of its smaller cousins. This is another form of scale, not just physical scale, but observational scale. The farther and more extreme an object is, the more we have to rely on indirect methods and models. Another interesting comparison is with the black holes predicted by theory but not yet observed. Some models of the early universe suggest that primordial black holes might exist, formed not from stars but from density fluctuations shortly after the Big Bang. These could in theory range in size from tiny to enormous. TON 618 is not thought to be a primordial black hole, but comparing its mass and properties to these theoretical objects helps constrain what kinds of formation processes are plausible. So even in comparison to things that are not yet known to exist, TON 618 plays a role. All of these comparisons taken together create a kind of relational map. TON 618 is not just big, it is bigger than most supermassive black holes, smaller than galaxies in size but larger in mass than any single star or cluster of stars, more energetic than most galaxies, and more distant than the black holes we can study in detail. This map helps turn the abstract into something more structured. There is also a quieter, more personal effect of making these comparisons. It can shift how you think about your own place in the universe. The Earth orbits a star that is one of hundreds of billions in a galaxy, that is one of hundreds of billions in the observable universe. That galaxy contains a black hole that is massive, but not nearly as massive as TON 618. So when you compare these layers, you start to see how many levels of scale exist between everyday life and the most extreme objects we know. This is not about making anything feel insignificant. It is about appreciating the range of what exists. TON 618 becomes a reference point, a kind of landmark at the high end of the scale, much like Mount Everest is a landmark in the range of mountains on Earth. Most mountains are not that tall, but knowing that Everest exists helps define what tall can mean. In the same way, knowing that TON 618 exists helps define what massive can mean when it comes to black holes. Is scale just about size and mass? Or is it also about influence, reach, and the way different systems connect across space and time? Instead of beginning with a number or a name, it can be useful to start with a feeling. The quiet moment when you stand somewhere open, maybe near a shoreline or on a wide plain, and realize there is no obvious edge in sight. Your eyes move, but they do not find a boundary. There is just more space stretching outward, inviting and a little disorienting at the same time. That sensation, more than any measurement, is often what people mean when they talk about scale. In the universe, and especially in the case of something like TON 618, that feeling becomes the main guide, because the usual reference points fall away almost immediately. On Earth, scale is something we learn through contrast. A chair is small compared to a room. A room is small compared to a building. A building is small compared to a city. A city is small compared to a country. At each step, there is something larger nearby that helps define the size of the thing you're looking at. Even when you travel far, the planet itself remains a kind of ultimate reference point. You know, at least in the back of your mind, that you are still on the same sphere, still under the same sky. In deep space, that hierarchy does not hold in the same way. There is no obvious floor or ceiling. There is no universal landmark that everything else can be measured against. So when we talk about the scale of TON 618, what we are really talking about is a relationship rather than a size. It is large compared to other black holes. It is small compared to galaxies. It is powerful compared to stars. It is subtle compared to galaxy clusters. It sits somewhere in a web of comparisons that only makes sense when you trace the connections between different kinds of cosmic structures. This is what it means to talk about scale in a universe without a fixed frame of reference. You're always measuring one thing against another, never against an absolute. Astronomers are very aware of this. That is why so many of the quantities used in astrophysics are expressed in relative terms. Masses are often given in units of the sun's mass. Distances are given in light years or parsecs. Brightness is compared to the luminosity of known objects. These units are not chosen because they are perfect. They are chosen because they are familiar within the context of the field. They provide a shared language. But even within that language, there is an awareness that everything is floating in relation to everything else. Take the idea of distance again. A light year is a convenient unit for talking about the separation between stars and galaxies. But a light year itself is defined by the speed of light and the length of a year, both of which are tied to the specific conditions of our corner of the universe. The speed of light is a fundamental constant, but the year is based on the Earth's orbit around the Sun. So even this cosmic unit is anchored indirectly to a small planet circling an ordinary star. When you say TON 618 is billions of light years away, you're layering one reference on top of another. You're measuring a vast cosmic separation using a unit that ultimately traces back to the movement of Earth around the Sun. This layering is not a flaw. It is a reflection of how all measurement works. You always start from where you are. In a universe without an absolute scale marker, everything becomes a network of relationships. This becomes especially clear when you think about how astronomers determine the size and mass of something like TON 618. There is no direct way to reach out and measure it. Instead, they look at how fast gas moves around it. They look at how light is bent by its gravity. They look at how bright its quasar is, and how that brightness changes over time. Each of these observations provides a piece of a larger relational puzzle. Speed tells you something about gravity. Gravity tells you something about mass. Brightness tells you something about energy output. Energy output tells you something about how much material is falling inward. So the scale of the black hole emerges not as a single, direct measurement, but as a consistent story told by multiple interconnected signals. This way of building understanding can feel very different from measuring something with a ruler or a scale. There is no moment where you say, here is the answer. Instead, there is a gradual convergence, where different lines of evidence start to point toward the same range of values. This process itself is a kind of scale. It operates over years or decades of observation, across multiple telescopes and research teams, and through generations of models and revisions. So when we talk about the scale of TON 618, we're also talking about the scale of the effort required to understand it. Another layer of this idea comes from the way space and time are intertwined. In everyday life, distance and time feel like separate things. You can be close to something in space but far from it in time, like an old photograph of a place you visited years ago. Or you can be far in space but close in time, like a live video call with someone on the other side of the planet. In astronomy, distance and time are linked in a much more direct way. Because light takes time to travel, looking farther into space means looking farther into the past. So the scale of TON 618 is not just about how big it is also about when it is. The version of TON 618 we observe today is a version that existed billions of years ago. Its mass, its brightness, its environment may have changed since then. The black hole might have grown larger or quieter. The host galaxy might have merged with others or formed new stars. So when we describe its scale, we're always describing a moment in its history rather than a timeless property. This temporal dimension adds another reference point, or rather, Another lack of one. There is no universal now in the universe. Every observation is tied to the time it takes light to travel. This means that scale is always four-dimensional. It includes not just size and distance, but also age. In this sense, TON 618 is large, not only because of its mass, but because of the span of cosmic history it represents. It is a marker of what the universe was capable of building at a particular stage in its evolution. Another way to approach this is to think about the idea of influence rather than size. On Earth, size and influence often go together. A larger building usually houses more people. A larger city usually has more impact on a region. In space, this relationship can be less straightforward. A small star can have a strong influence on a nearby planet, shaping its climate and potential for life. A massive galaxy cluster can have a relatively subtle effect on any single star within it, even though its total mass is enormous. TON 618 is interesting because its influence is not confined to a small neighbourhood. The energy it releases can affect conditions across its host galaxy. In that sense, its scale is not just about how much mass it has, but about how far its reach extends. This introduces a different kind of reference point. Instead of measuring the black hole against other objects of similar type, you measure it against the region of space it can shape. From that perspective, TON 618 becomes a kind of central node in a larger system, a point where gravity and energy flow outward into the surrounding environment. This is a relational view of scale. It asks not how big is this, but what does this connect to? Another interesting aspect of scale in a reference-free universe is how it changes depending on where you place your attention. If you focus on the event horizon of TON 618, the scale is measured in light hours or light days. You're thinking about the boundary where space and time behave in extreme ways. If you shift your attention to the host galaxy, the scale jumps to tens of thousands of light years. Now you're thinking about star formation, gas clouds, and the overall shape of a galaxy. If you move out even farther, to the cosmic web, the scale becomes millions or billions of light years. The black hole becomes a tiny point in a vast network of matter and energy. So the scale of TON 618 is not a single value. It is a set of nested scales, each relevant to a different question. This nesting can make the idea of true scale feel elusive. True for what? True for the physics near the event horizon? True for the evolution of the galaxy? True for the structure of the universe as a whole? Each of these contexts gives a different answer. Another subtle point is that scale is often tied to resolution, the level of detail you can see. With the naked eye, the moon looks like a smooth, bright disk. With a telescope, you see craters and mountains. With a spacecraft, you see boulders and dust. The object does not change. Your ability to resolve detail does. The same is true for TON 618. From a distance, it is a point of light. With spectroscopy, it becomes a system of moving gas and dust. With more advanced instruments, it becomes a structured environment with layers, flows, and interactions. So the scale of the black hole grows in a sense as your tools improve, not because it becomes bigger, but because more of its complexity becomes visible. This is another reason why the idea of a fixed scale can feel misleading. What you perceive as large or small depends on what you can see and measure. There is also a cultural dimension to this. Different fields of science have different intuitive scales. A biologist might think in terms of cells, tissues, and organisms. A geologist might think in terms of layers of rock and spans of millions of years. An astronomer might think in terms of light years and solar masses. Each of these perspectives comes with its own reference points. When you step into astronomy, and especially into the study of objects like TON 618, you're stepping into a scale where even the usual astronomical reference points start to feel small. This can be both challenging and freeing. Challenging because it stretches the limits of intuition. Freeing because it allows you to think beyond the immediate and the local. Another way to look at scale in this context is to think about proportion. Proportion is about how parts relate to a whole. In a human body, the head, the torso and the limbs have certain relative sizes. If those proportions change too much, the body looks unfamiliar or even unrecognizable. In a galaxy, the central black hole is usually a very small fraction of the total mass. Its event horizon is tiny compared to the galaxy's diameter, yet its influence can be significant. TON 618 seems to push these proportions. The black hole appears unusually large relative to its host galaxy, at least based on current estimates. This raises questions about whether the usual proportions apply in all eras of the universe's history. Perhaps in the early universe, black holes and galaxies grew at different rates, leading to different relative sizes. So scale here is not just about absolute numbers, it is about ratios and relationships. This idea of proportion extends even further into the way we think about ourselves. A human is small compared to a planet, but large compared to a cell. Both of those statements are true. The scale you choose to focus on changes the story you tell. TON 618 is enormous compared to a star, but small compared to a galaxy cluster. Both of those statements are also true. So when we talk about the true scale of TON 618, we are really choosing a frame of reference. We're deciding which comparison matters for the question we're asking. If the question is about black hole physics, then TON 618 is one of the largest examples known. If the question is about the structure of the universe, then TON 618 is a tiny node in a vast network. Neither view is wrong. They are simply focused on different levels of the same system. There is also an interesting feedback between scale and meaning. Objects often feel more meaningful when they're closer to our own scale. A tree in your yard can feel more emotionally significant than a distant mountain you have never seen. A star in the sky can feel more personal than a distant galaxy. TON 618 is so far removed from human scale that it can feel almost purely intellectual. It is something you think about rather than something you feel. And yet, by placing it in a network of comparisons, by connecting it to the Sun, to the Milky Way, to the broader universe, it becomes part of a story that includes us as well. The Sun's mass becomes a stepping stone to understanding the black hole's mass. The Milky Way's structure becomes a stepping stone to understanding the host galaxy. Our own place in the universe becomes part of the chain of reference. So even in a universe without an absolute reference point, we create our own, starting from where we are. There is something quietly reassuring about this. It suggests that scale is not just an external property of the universe. It is also a relationship between the universe and the observer. You bring your own frame of reference to whatever you look at, whether it is a small object on a table or a black hole billions of light years away. Long before any measurement is written down or any image is processed into colour and contrast, gravity is already at work, quietly shaping the stage on which everything else happens. It does not announce itself with sound or light. It does not need a signal or a marker. It simply curves, pulls and guides, setting the paths that matter and energy will follow. When the object involved is something like TON 618, that quiet shaping becomes a dominant feature of the entire system, reaching far beyond the immediate region of the black hole itself. To begin understanding how gravity behaves around such a massive object, it helps to move away from the idea of gravity as an invisible rope, or a force that reaches out and tugs. That picture works well enough for everyday life, where the Earth pulls you toward the ground and keeps the Moon in orbit. But in modern physics, gravity is described in a different way. It is not a force acting across space. It is a property of space itself. Mass and energy tell space how to curve, and curved space tells matter and light how to move. This way of thinking can feel abstract at first, but it becomes more tangible when you imagine a stretched fabric. Place a heavy object in the centre, and the fabric dips. Roll a smaller object nearby, and it will follow a curved path around the dip. The heavier the central object, the deeper and steeper the curve. This analogy is limited, but it captures an important idea. Around TON 618, the dip in the fabric of space is not just a gentle slope. It is an extreme curvature that changes the very rules of motion. Far from the black hole, gravity behaves in a way that is familiar. Gas clouds and stars follow roughly elliptical orbits. Light travels in nearly straight lines. Time passes at a rate that is, for practical purposes, the same as it does for us here on Earth. As you move closer, those assumptions start to loosen. The paths of objects begin to curve more sharply. Light no longer travels in straight lines, but follows the bent geometry of space. Time itself begins to slow down relative to distant observers. This is not a metaphor. It is a measurable effect. Even around Earth, which is a very modest mass by cosmic standards, time passes slightly more slowly at the surface than it does in orbit. This difference is small, but it is large enough that GPS satellites have to account for it to keep their clocks in sync with those on the ground. Around TON 618, the same effect exists, but on a vastly larger scale. Near the event horizon, time would pass so slowly compared to a distant observer that the difference becomes dramatic. From the outside, an object falling toward the black hole would appear to slow down and fade, never quite crossing the boundary. From the object's own perspective, however, time would continue normally, at least until it reached regions where our current understanding of physics breaks down. This difference in the flow of time is one of the most counterintuitive aspects of gravity at this scale. It means that the black hole is not just a place where things fall in, it is a place where the relationship between past, present and future is altered. Another way gravity shapes the space around TON 618 is through its effect on light. When light passes near a massive object, its path bends. This is called gravitational lensing. The black hole itself is usually too small in angular size from our perspective to produce a dramatic lensing effect on its own. But the combined mass of the black hole and its host galaxy can bend the light of more distant objects, creating subtle distortions in the images we see. These distortions can appear as stretched shapes, arcs, or multiple images of the same background object. For TON 618, lensing is not the main feature that draws attention, but it is part of the gravitational environment. The region around the black hole and its galaxy contributes to the overall curvature of space in that part of the universe. This bending of light is another way astronomers infer the presence and distribution of mass, even when that mass is not directly visible. Gravity also shapes the motion of gas on every scale around TON 618. In the outer parts of the host galaxy, gas and stars move under the combined gravitational influence of the galaxy's stars, dark matter, and the central black hole. The black hole's contribution becomes more important as you move inward. At some distance, the gravity of the black hole begins to dominate over the gravity of the surrounding galaxy. This region is sometimes called the black hole's sphere of influence. Within this sphere, the motion of stars and gas is primarily determined by the black hole's mass. For a black hole as massive as TON 618, this sphere of influence is large. It can extend across significant portions of the galaxy's central region. This means that the black hole is not just affecting the very inner accretion disk, it is shaping the dynamics of the galaxy's core. Gas clouds within this region tend to settle into orbits that reflect the black hole's gravitational pull. Over time, interactions between these clouds, combined with processes like cooling and turbulence, can funnel material inward, feeding the accretion disk. So gravity acts not just as a sink, pulling matter in at the last moment, but as a guide, shaping the large-scale flow of material toward the centre. Another important aspect of gravity around TON 618 is how it interacts with rotation. The black hole is almost certainly spinning. That spin does not just affect the black hole itself, it affects the space around it. This effect, known as frame dragging, means that space is literally pulled around by the rotating mass. Objects near the black hole find that their natural paths are influenced by this twisting of space. For the accretion disk, this can have significant consequences. If the disk is aligned with the black hole's spin, the inner regions can settle into stable orbits close to the event horizon. If it is misaligned, the disk can become warped, with different parts trying to align themselves with the black hole's equatorial plane. This process, called the Bardeen-Peterson effect, can cause the inner disk to tilt and twist relative to the outer disk. Over time, the system may settle into a configuration where the inner and outer regions are aligned, but the path to that state can be complex and dynamic. For TON 618, the scale of this effect is enormous. The region where frame-dragging matters extends across distances that would be measured in light days or light weeks, rather than kilometres. So gravity here is not just a central pull, it is a sculptor of structure, shaping the geometry of the disk and influencing how material moves on large scales. Another layer of gravitational influence comes from the interaction between the black hole and the dark matter in the host galaxy. Dark matter does not interact with light, but it does interact gravitationally. It forms a halo around galaxies, contributing most of their mass. This halo shapes the overall gravitational potential in which the galaxy and the black hole reside. TON 618 sits within this dark matter environment. The combined gravitational field of the dark matter halo and the visible matter of the galaxy sets the stage for how gas flows on large scales. So the black hole's gravity is part of a larger gravitational landscape. It dominates in the inner regions, but it is embedded in a field shaped by much more mass spread across a much larger volume. This layered gravitational structure is another reason scale becomes such a central theme. Different physical processes dominate at different distances from the black hole, but they are all connected through the same underlying geometry of space. Another intuitive challenge is the idea that gravity affects not just motion, but also energy. When matter falls into a gravitational well, it gains kinetic energy as it speeds up. That energy is often converted into heat through collisions and friction. In the accretion disk around TON 618, this process is extremely efficient. The deeper the gravitational well, the more energy can be extracted from infalling matter before it crosses the event horizon. This is why the quasar powered by TON 618 is so luminous. The black hole's gravity is converting mass into energy with remarkable efficiency. This connection between gravity and energy means that the black hole's influence is not confined to shaping orbits. It also shapes the thermal and radiative environment of the entire system. Another way to see gravity's reach is through the phenomenon of tidal forces. Tidal forces arise because gravity is stronger on the side of an object closer to a massive body than on the far side. On Earth, this effect is what creates the tides in the oceans under the influence of the moon and the sun. Near a black hole, tidal forces can become extreme. They can stretch and compress objects, potentially pulling them apart in a process sometimes called spaghettification. For TON 618, the situation is somewhat different from that around smaller black holes. Because the event horizon is so large, the gradient in the gravitational field at the horizon is actually less steep. This means that, in theory, an object crossing the event horizon of a very massive black hole might not experience strong tidal forces at that moment. The most extreme stretching would occur deeper inside, closer to the central singularity. This is another counterintuitive aspect of scale. A bigger black hole can be in some ways gentler at its boundary than a smaller one. Of course, this is a theoretical consideration. No physical object could survive the journey to test it, but it highlights how gravity's behaviour changes with mass and size. Another subtle way gravity shapes space around TON 618 is through its effect on the surrounding cosmic environment. The galaxy hosting the black hole is part of a larger structure, possibly a group or cluster of galaxies connected by filaments of matter. The gravitational influence of these larger structures can affect how gas flows into the galaxy, potentially providing fuel for the black hole over long periods of time. So the black hole's growth is not just a local process, it is connected to the dynamics of the larger cosmic web. In this sense, gravity operates on multiple levels at once. It shapes the immediate environment of the black hole, it shapes the structure of the host galaxy, and it shapes the distribution of galaxies on the larger scales. TON 618 sits at the intersection of these levels. Another aspect worth considering is how gravity affects our ability to observe the system. The extreme curvature of space near the black hole can alter the paths of light emitted from the accretion disk. This means that the images and spectra we observe are not straightforward views of the disk's structure. They are views that have been distorted by the black hole's gravity. For example, light emitted from the far side of the disk can be bent around the black hole and reach us, allowing us to see parts of the disk that would otherwise be hidden. This gravitational lensing on a small scale can create features in the spectrum and brightness patterns that need to be accounted for when interpreting the data. So gravity shapes not only the physical system, but also the information we receive about it. This adds another layer of complexity to the process of understanding TON 618. Astronomers have to disentangle the intrinsic properties of the disk and the galaxy from the distortions introduced by the black hole's gravitational field. Another way to think about this is in terms of reference frames. In everyday life, we tend to assume there is a single shared now and a single shared sense of space. In the relativistic environment around a black hole, that assumption breaks down. Different observers, at different distances and in different states of motion, will measure different times and distances for the same events. This means that the description of what is happening near TON 618 depends on where you are and how you're moving. From far away you see a quasar shining steadily. From closer in you might see intense, rapidly changing patterns of light and motion. From within the accretion disk, the experience would be something else entirely, shaped by extreme speeds and strong gravitational fields. This multiplicity of perspectives is another way gravity complicates the idea of a single, simple picture of the system. There is also a deeper theoretical layer to all of this. At the very centre of the black hole, according to our current understanding, lies a singularity, a point where density becomes infinite, and the equations of general relativity break down. This is a region where our current description of gravity no longer works. We do not have a complete theory that combines general relativity with quantum mechanics to describe what happens there. So gravity around TON 618 leads us not just into extreme physical conditions, but into the limits of our knowledge. The event horizon marks the boundary between the region we can in principle observe and the region we cannot. Everything that happens beyond that boundary is hidden from the rest of the universe. This creates a kind of natural horizon for understanding as well. We can describe the curvature of space outside the horizon. We can model the behaviour of matter and light in the accretion disk. We can infer properties of the black hole from its influence on its surroundings. But the very centre remains inaccessible, not just physically, but conceptually. This adds a quiet sense of depth to the idea of gravity shaping space. It is not just shaping a visible structure, it is shaping the boundary between what can be known and what cannot. Another interesting perspective comes from thinking about how gravity ties into the broader expansion of the universe. On the largest scales, space itself is expanding. Galaxies are moving away from each other as the fabric of the universe stretches. On smaller scales, gravity can overcome this expansion and bind systems together. Galaxies remain intact. Clusters of galaxies remain bound. TON 618 exists within this balance. Its host galaxy is held together by gravity, even as the universe expands around it. So gravity here is part of a cosmic tension between binding and separation, between attraction and expansion. This tension shapes the large-scale structure of the universe, creating the cosmic web of filaments and voids. TON 618, as a massive concentration of matter, plays its own small role in this structure, anchoring its local region of space. As you reflect on all of this, the idea of gravity around TON 618 begins to feel less like a single phenomenon and more like a network of effects. It curves space, it slows time, it bends light, it guides motion, it releases energy, it shapes structure, it marks the boundary of knowledge. All of these are different expressions of the same underlying property of mass and energy interacting with the geometry of the universe. This multi-layered influence is part of what makes the idea of a giant feel more than just a description of size. It describes a presence, a central role in a system of relationships that extend from the smallest scales near the event horizon to the largest scales of the cosmic web. And yet, even with all this reach and complexity, TON 618 is still one object among many in a universe filled with structures at every level of scale. There is a quiet humility in that thought. The black hole is extreme, but it is not unique in the sense of being outside the laws of physics. It follows the same principles that govern every other mass and every other motion, just in a regime where those principles produce especially dramatic results. How did something like TON 618 come to be? How did it gather so much mass over cosmic time? What does its current state tell us about the conditions in the early universe and the processes that drive growth on the larger scales? Long after the first light from TON 618 began its journey toward Earth, the universe itself continued to change in ways that would eventually make that light understandable. Galaxies formed, stars were born and died, heavy elements spread through space, and on a small planet orbiting an ordinary star, instruments were built that could catch those ancient signals and turn them into insight. When James Webb started adding its own data to this long chain of observation, it did more than sharpen a picture. It added a sense of timeline to an object that already seemed to exist outside of ordinary time. To talk about the growth and age of something like TON 618, it helps to begin with a simple idea. Nothing in the universe appears fully formed. Stars gather from clouds of gas. Planets assemble from disks of dust and rock. Galaxies build themselves through slow accumulation and occasional dramatic mergers. Black holes, even the most massive ones, follow the same general pattern. They grow. What makes TON 618 so interesting is not just that it is large, but that it appears to have become large very early in the history of the universe. The light Webb observes from this quasar left its source more than 10 billion years ago. At that time, the universe was less than a third of its current age. That places TON 618 in a period when galaxies were still settling into their modern forms, when star formation was more intense, and when the cosmic environment was richer in raw material. So one of the first questions Webb's data helps address is not, how big is TON 618? But, how did it get that big so soon? To approach that, astronomers look for clues in the surrounding galaxy. Growth leaves traces. It shapes the distribution of gas and dust. It influences the chemical composition of the environment. It affects how stars form and how energy flows. Webb's ability to detect infrared light is crucial here, because it allows astronomers to see through dust and measure the glow of both old and young stars. From this, they can estimate how much stellar mass the galaxy has, and how actively it is forming new stars. If a galaxy is forming stars rapidly, it likely has large reservoirs of cold gas. That same gas can also feed the central black hole, so a high star formation rate can be a sign of a rich environment for black hole growth. For TON 618's host galaxy, Webb's data suggests a complex picture. There are indications of significant amounts of dust and gas, which implies that star formation has been active. But there are also signs that the intense energy output of the quasar may be heating or pushing away some of that gas, potentially slowing down the formation of new stars in certain regions. This balance between feeding and feedback is a key part of understanding growth. The black hole grows by pulling in matter, but as it grows and shines more brightly, it can begin to disrupt the very environment that feeds it. Radiation and winds from the quasar can heat gas, making it harder for that gas to collapse into stars or fall inward toward the centre. So growth is not a simple, one-directional process. It is a negotiation between gravity pulling material in and energy pushing material out. Webb's observations of the temperature and distribution of dust help map where this negotiation is taking place. Warmer dust farther from the centre suggests that the quasar's influence reaches deep into the galaxy. Cooler regions may indicate areas where gas remains relatively sheltered, potentially continuing to form stars. Another clue about growth comes from the chemical composition of the gas around TON 618. Heavy elements like carbon, oxygen and iron are produced in stars. The more generations of stars a galaxy has gone through, the more enriched its gas becomes with these elements. By analysing the spectral lines in the infrared, astronomers can estimate the abundance of these elements in the gas surrounding the quasar. Webb's data suggests that the environment around TON 618 is already quite enriched, even at this early cosmic time. This implies that the galaxy has experienced multiple cycles of star formation and stellar death. This enrichment provides a rough sense of age, not in terms of a specific number of years, but in terms of developmental stage. The galaxy is not in its very first phase of star formation. It has a history. That history in turn sets the stage for black hole growth. More stars mean more heavy elements. More heavy elements mean more efficient cooling of gas. More efficient cooling means gas can collapse more easily, forming both stars and feeding the central black hole. So the chemical signals Webb detects are part of a chain of cause and effect that stretches back through the galaxy's past. Another aspect of Webb's contribution is its ability to study the structure of the quasar's light in fine detail. The shape of the spectrum, including both the bright emission lines and the underlying continuum, carries information about how much material is falling into the black hole and how efficiently that material is being converted into energy. From this, astronomers can estimate the accretion rate, the amount of mass the black hole is gaining per year. For TON 618, these estimates suggest a high, but not extreme, accretion rate relative to its mass. This means that, at the time we are observing it, the black hole is still growing, but it is not in the most intense phase of feeding it might have experienced. This hints at a longer, steadier growth history rather than a single dramatic burst. Of course, this is a snapshot. We are seeing the black hole at one moment in its long life. It may have gone through periods of much more rapid growth earlier, when the galaxy was even richer in gas, or when mergers brought in fresh material. Webb's data does not show us those earlier phases directly, but it provides context that helps make them plausible. Another way to think about growth is through the size and structure of the accretion disk itself. A large extended disk suggests a steady supply of material over long timescales. If the black hole were fed only in short sporadic bursts, the disk might appear more chaotic or truncated. Webb's infrared observations of the dust and gas around TON 618 suggest a relatively well-developed structured environment. This supports the idea that the system has had access to material over an extended period. There is also the question of mergers. Galaxies in the early universe were closer together and more likely to collide. When galaxies merge, their central black holes can eventually merge as well, or at least influence each other's growth by disturbing gas and driving it toward the centre. Webb's sensitivity allows astronomers to look for faint signs of past interactions, such as tidal streams of stars or asymmetries in the host galaxy structure. While the data is still being analysed, any evidence of such features would support a growth history that includes mergers as well as steady accretion. Another clue about age comes from comparing TON 618 to other quasars at similar and different redshifts. By building a sample of objects at different distances, astronomers can look for trends in black hole mass, accretion rate, and host galaxy properties over cosmic time. TON 618 appears to be among the more massive black holes at its epoch. This suggests that it is not a typical example, but one that represents the upper end of what was possible at that stage in the universe's development. This raises an interesting possibility. Perhaps the conditions that allowed TON 618 to grow so large were rare. Maybe its host galaxy formed in a particularly dense region of the cosmic web, where gas was abundant and mergers were frequent. Webb's ability to detect the larger scale environment around distant galaxies can help test this idea. By looking for nearby galaxies or filaments of gas, astronomers can infer whether TON 618's host sits in an especially rich neighbourhood. Another angle on growth and age comes from considering the black hole's spin. The spin of a black hole can provide hints about its growth history. If a black hole grows primarily through steady accretion from a disk that is consistently aligned in one direction, it can spin up to very high speeds. If it grows through a series of mergers or chaotic accretion events from different directions, its spin may be more moderate. Webb's data, combined with observations at other wavelengths, can help constrain models of the inner accretion disk, which in turn can hint at the black hole's spin. For TON 618, there are indications that it may be spinning rapidly, which would be consistent with a history of prolonged aligned accretion. But this remains an area of active research rather than a settled conclusion. Another subtle indicator of age is the size of the region influenced by the quasar's energy. If the quasar has been active for a long time, its radiation and winds will have had more time to shape the surrounding galaxy. You might expect to see larger, more developed outflows or more extended regions of heated dust. Webb's observations of warm dust and gas at significant distances from the centre suggest that TON 618's quasar has been influencing its environment for a substantial period. This does not give a precise age, but it adds to the picture of a system that has been active and impactful for a long stretch of cosmic time. There is also the broader context of cosmic history to consider. The universe went through a period known as the Cosmic Dawn, when the first stars and galaxies formed. After that, there was an era of rapid growth, when star formation and black hole activity peaked. TON 618, as we observe it, appears to sit near the tail end of this peak period. It represents a system that has already gone through much of its most active growth phase. So in terms of age, it is not a newborn, it is a mature system, even at a time when the universe itself was relatively young. This layered sense of age can be hard to hold in the mind. TON 618 is billions of years old, but so is most of the universe. It is ancient by human standards, but it is still part of an ongoing story of cosmic evolution. Another way to think about this is in terms of opportunity. The early universe provided a unique set of conditions. Gas was more plentiful, galaxies were more compact, mergers were more common. These conditions created opportunities for black holes to grow quickly. As the universe expanded and evolved, those opportunities became less frequent. Gas became more spread out. Galaxies settled into more stable structures. Growth slowed. TON 618 appears to be a product of that earlier, more active era. Its size and power suggest that it took advantage of those conditions in a way that most systems did not. Webb's data helps reinforce this idea by showing the richness of the environment around the quasar and the signs of sustained activity. Another interesting perspective comes from looking at the relationship between the black hole and the stars in the galaxy. In many systems, the mass of the black hole and the mass of the galaxy's central bulge grow together over time. But TON 618 seems to challenge this pattern. If the black hole is as massive as current estimates suggest, its host galaxy would need to be extraordinarily large to maintain the usual ratio. Webb's observations of the galaxy's infrared light provide a way to estimate its stellar mass more accurately. Early results suggest that the black hole may indeed be ahead of its galaxy in terms of growth. This implies a growth history where the black hole either formed early and grew quickly, or where it experienced particularly efficient feeding, perhaps driven by a series of mergers or by a very favourable position in the cosmic web. This kind of asymmetry adds another dimension to the idea of age. The black hole and the galaxy may not be the same age in terms of developmental stage, even though they formed around the same time. Another clue about growth comes from looking at the variability of the quasar. Changes in brightness can reflect changes in the accretion rate. By monitoring these changes over time, astronomers can infer something about the stability of the feeding process. For TON 618, the variability appears to be relatively modest, which is consistent with a large, massive disk that smooths out short-term fluctuations. This supports the idea of steady, long-term growth rather than a series of violent bursts. Of course, this does not rule out dramatic events in the more distant past. It simply suggests that, at the time we are observing it, the system has settled into a more stable phase. Another layer of interpretation comes from comparing TON 618 to theoretical models of black hole formation. Some models suggest that the first black holes formed from the collapse of very massive pristine gas clouds in the early universe, creating seed black holes that were already quite large. Others suggest that black holes started as remnants of the first stars and grew through accretion and mergers. TON 618's size and early appearance put pressure on models that rely only on small seeds and slow growth. It suggests that either the seeds were larger than some models assume, or that growth was extremely efficient, or both. Webb's data on the surrounding galaxy and its environment can help test these ideas by revealing how much gas was available and how the galaxy was structured. There is a quiet sense of scale in this as well. The growth of TON 618 is not just a story about one object. It is a story about the conditions of the early universe, about how matter was distributed, about how galaxies formed, and about how gravity shaped everything that followed. So when we talk about what Webb's data suggests about the growth and age of TON 618, we are really talking about a window into a much larger process. The black hole becomes a kind of marker, a way of tracing the flow of cosmic history. It shows that, given enough time and the right conditions, gravity can gather matter on a scale that seems almost implausible. It shows that the early universe was capable of building structures that still challenge our understanding today. And it shows that, even now, billions of years later, the light from those early structures can still reach us, carrying information about how they came to be. What does an object like this do to our theories? How does it change the way we categorize and understand these extreme regions of space? At a certain point in scientific exploration, an object stops being just an example and starts becoming a problem in the best possible sense of the word. Not a problem because it is confusing, but because it refuses to fit comfortably inside the boxes we have built for understanding. TON 618 sits squarely in that category. Its existence does not overturn everything we know about black holes, but it quietly rearranges the furniture. It forces adjustments. It asks for patience. It changes emphasis. And in doing so, it reshapes how black holes are thought about, discussed and modelled across astronomy as a whole. For a long time, black holes were treated as endpoints. A star collapses, gravity wins, a compact object remains. Even when supermassive black holes were discovered at the centres of galaxies, the framing often stayed similar. These were seen as anchors, static features around which galaxies evolved. Important? Yes, but not especially dynamic in a conceptual sense. TON 618 disrupts that framing. It does not behave like a passive anchor. It behaves like a long-term participant in cosmic evolution, one whose growth, energy output and timing cannot be separated from the history of its galaxy or the larger universe around it. That alone shifts the way black holes are understood, from quiet leftovers of collapse to active, evolving systems. One of the first ways TON 618 changes thinking is by challenging assumptions about limits. For years, astronomers worked with the idea that there might be a practical upper boundary on black hole mass, not a hard theoretical wall, but a limit set by available material and feedback. As black holes grow, they release energy. That energy heats surrounding gas, making it harder for more matter to fall in. Growth slows, balance is reached. TON 618 sits uncomfortably close to where that balance was thought to become unavoidable. Its mass suggests that, at least in some environments, black holes can keep growing far longer and far more efficiently than expected. This does not mean the models were wrong. It means they were incomplete. They may describe typical cases well, but they do not capture the full range of what is possible. This pushes black hole science toward thinking in terms of distributions rather than averages. Instead of asking, how big do black holes usually get, the more useful question becomes, under what conditions do black holes get extremely large? That shift matters. It moves attention away from generic growth and toward environmental factors, cosmic timing, and rare but important pathways. Another conceptual change comes from how TON 618 reframes the relationship between black holes and galaxies. For a long time, the idea of co-evolution dominated the conversation. Black holes and galaxies grow together. Their masses track each other. Feedback regulates both star formation and black hole feeding. TON 618 complicates this picture. If its black hole truly outweighs what we would expect based on the mass of its host galaxy, then the relationship between black hole growth and galaxy growth cannot be as rigid as once thought. At least not in the early universe, and not in every case. This does not eliminate the idea of co-evolution, but it loosens it. It suggests that black holes can, under certain conditions, grow ahead of their galaxies rather than alongside them. That possibility has broad implications. It means black holes may sometimes act as drivers rather than responders. Instead of growing because the galaxy grows, they may grow first and then shape the galaxy's future by regulating gas and star formation. TON 618 provides a concrete example that makes this idea difficult to ignore. Another shift happens in how astronomers think about black hole formation itself. There are multiple proposed pathways for creating the first black holes. Some involve the remnants of the first stars, others involve the direct collapse of massive gas clouds. Each pathway leads to different starting masses, different growth rates, and different timelines. TON 618 strains models that rely only on small initial seeds and gradual growth. To reach tens of billions of solar masses within a few billion years, either the starting point must have been unusually large, the growth unusually efficient, or the environment unusually favourable, possibly all three. This pushes researchers to take direct collapse scenarios more seriously, or to consider combinations of pathways rather than single mechanisms. It also encourages more attention to the earliest phases of galaxy formation, when gas densities, temperatures and radiation fields were very different from what we see today. In that sense, TON 618 acts like a fossil from a particular era of cosmic history, preserving evidence of processes that are rare or no longer active in the modern universe. Another important change comes from how TON 618 affects the way mass itself is discussed in black hole science. Before objects like this were identified, supermassive black holes were often talked about as a category, with masses ranging from millions to billions of suns. TON 618 stretches that range so far that the category itself starts to feel too broad. There is a growing recognition that the upper end of the mass range behaves differently, not just quantitatively but qualitatively. For example, extremely massive black holes have very large event horizons, which changes the character of tidal forces, accretion dynamics, and timescales. Processes that happen quickly around smaller black holes unfold more slowly and smoothly around giants like TON 618. This means that scaling laws derived from smaller systems cannot always be applied directly. TON 618 forces a reconsideration of where those scaling laws hold and where they break down. That has ripple effects across the field, because many models are built by extrapolating from systems that are easier to observe. When an object at the extreme end refuses to follow the same patterns, it highlights the need for caution. Another way TON 618 changes thinking is by altering the role of rarity. In science, rare objects can sometimes be dismissed as oddities, interesting but not representative. TON 618 resists that dismissal because it sits at a boundary that matters for theory. If even one black hole can grow this large, then any comprehensive theory of black hole growth must be able to explain it. Rarity does not reduce importance when the object challenges fundamental assumptions, so TON 618 becomes a constraint. Any model that cannot accommodate it is incomplete. This elevates its status from curiosity to benchmark. Another shift comes from how time is treated in black hole studies. Black holes are often described in terms of their present properties: mass, spin, accretion rate. TON 618 encourages a more explicitly historical view. Its size makes sense only when considered in the context of the early universe. The timing of its growth is as important as the amount of growth itself. This pushes black hole science closer to cosmology, where time and evolution are central. Black holes are no longer just objects in galaxies. They are actors in the history of the universe. That integration deepens the field. It connects black hole studies to questions about reionization, early star formation, and the emergence of large-scale structure. Another important change involves how astronomers think about efficiency. TON 618's luminosity and inferred accretion history suggests that black hole feeding can be remarkably efficient over long periods. This efficiency has implications for how matter behaves under extreme gravity and radiation. It suggests that, under the right conditions, accretion disks can remain stable, structured and productive for extended timescales, even as they channel enormous amounts of mass inward. This challenges older mental pictures of accretion as chaotic or self-limiting. Instead, it points toward accretion as a process that can, in some cases, become self-organizing, maintaining a balance between inflow and feedback that allows growth to continue. That idea has consequences not just for black holes, but for how energy flows through galaxies more generally. TON 618 also changes how astronomers think about observation itself. Because it is so distant and so extreme, everything known about it comes from indirect signals, spectra, infrared emission, subtle shifts in light. This reinforces the idea that black hole science is, by necessity, an interpretive discipline. It relies on inference rather than direct inspection. TON 618 shows both the power and the limits of this approach. It demonstrates how much can be learned from light alone, but it also highlights the uncertainties that remain. That awareness encourages humility in interpretation. It reminds researchers that even the best models are provisional. Another conceptual shift comes from the way TON 618 reframes the meaning of extreme. In popular discussions, black holes are often described as extreme by default. Everything about them seems dramatic, immense gravity, inescapable darkness, violent environments. TON 618 adds a layer to that narrative. It shows that there are degrees of extremeness even among black holes. What seems extreme when compared to everyday experience may turn out to be moderate when compared to the upper limits of what the universe can produce. This encourages more nuanced language and thinking. Instead of treating black holes as a single class of extreme objects, scientists increasingly think in terms of regimes, ranges, and transitions. TON 618 sits in a regime where familiar intuitions about black holes start to fail. Another subtle change involves how black holes are positioned within the story of cosmic structure. For a long time, galaxies were the primary units of structure in astronomy. Black holes were features within galaxies. TON 618 blurs that hierarchy. When a black hole becomes massive enough, its influence rivals that of the galaxy itself. Its energy output can shape star formation, gas distribution, and even the thermal state of intergalactic space nearby. This raises the possibility that, at certain epochs, black holes were among the primary architects of structure rather than secondary components. That idea does not replace galaxies as central players, but it elevates black holes to a more active role. Another change comes from the way uncertainty is treated. TON 618 exists at the edge of measurement. Its mass estimate has a range. Its host galaxy properties are still being refined. Its environment is complex. Instead of seeing this uncertainty as a weakness, black hole science increasingly treats it as a signal of depth. The uncertainties mark where new physics or new observational strategies may be needed. TON 618 acts as a guidepost for where future instruments and theories should focus. In that sense, it shapes not just understanding, but research direction. Another effect is psychological, though no less real. TON 618 shifts expectations. Once you know that black holes can reach this scale, smaller ones feel different. A billion solar mass black hole no longer feels like the ultimate extreme. It becomes part of a broader continuum. This does not diminish the significance of other black holes. It reframes them. The universe begins to look less like a place with a few extraordinary exceptions, and more like a place with a wide, continuous range of outcomes, shaped by conditions, timing, and chance. That perspective aligns well with how other areas of science operate. Biology, geology, and climate science all deal with distributions rather than singular ideals. Black hole science is moving in the same direction, and TON 618 accelerates that shift. There is also a philosophical dimension to this change. Black holes have often been used as symbols of finality, endpoints, places where information disappears, the ultimate limit. TON 618 complicates that symbolism. It is not an endpoint in the story of the universe. It is part of an ongoing process. It grew, it interacted, it influenced, it continues to change. Seeing black holes as evolving participants rather than static endpoints makes them feel less like cosmic punctuation marks and more like long-running sentences. Another way TON 618 changes thinking is by reinforcing the importance of context. No black hole exists in isolation. Its properties are shaped by its surroundings, its history, and its environment. TON 618 makes this explicit. Its size cannot be explained without reference to the early universe, its host galaxy, and the cosmic web around it. This encourages a more holistic approach to black hole studies, one that integrates galaxy evolution, cosmology, and high-energy physics rather than treating them as separate domains. Finally, TON 618 changes how black holes are taught and communicated. It provides a concrete example that stretches intuition without breaking it. It invites questions rather than closing them. Instead of presenting black holes as fully understood objects with a fixed set of properties, educators can point to TON 618 as evidence that the field is still evolving. That openness is valuable. It keeps curiosity alive. It reminds both scientists and listeners that understanding is provisional and that discovery is ongoing. TON 618 does not invalidate what was known before. It builds on it. It extends it. It adds weight to certain ideas and pressure to others. In doing so, it acts as a catalyst rather than a contradiction. As the picture continues to develop, TON 618 will likely remain an important reference point, not because it is the largest or the most distant forever, but because it marks a moment when black hole science had to widen its frame. The universe, once again, turned out to be more capable, more patient, and more expansive than expected. From the quiet vantage point of a small planet circling an unremarkable star, it might seem strange that something as distant and immense as TON 618 could say anything meaningful about where we belong. After all, there is no physical connection between daily life and a black hole billions of light years away. No signal from it shapes the weather. No gravity from it influences the orbit of the moon. No light from it brightens the night sky in a way that can be seen without instruments. And yet, when discoveries like this enter human awareness, they have a subtle effect that reaches far beyond the realm of astrophysics. They change how the universe is pictured, and in doing so, they change how the observer is placed within that picture. For most of human history, the cosmos was a backdrop rather than a landscape. The stars were lights in the sky, fixed and distant, arranged into patterns that told stories, guided travellers, and marked the passage of seasons. The Earth was the stage. Everything else was decoration. That view began to shift when telescopes revealed that the faint smudges in the night sky were not clouds or imperfections in vision, but entire galaxies, each containing more stars than there are grains of sand on a beach. Suddenly the universe was no longer a small, tidy space with a single central stage. It was a vast, layered environment, and Earth was one location among many. Discoveries like TON 618 push that shift even further. They introduce not just more space, but more depth. Not just more stars, but structures and processes that operate on scales of mass, energy, and time that have no direct parallel in everyday experience. When something like this enters the picture, the sense of a centre becomes harder to maintain. TON 618 does not sit at the centre of anything that matters to human life. It is not near the Milky Way. It is not near any familiar landmark in the sky. It exists in a distant region of the universe that would look no different from any other patch of darkness without the help of advanced instruments. And yet, through observation and analysis, it becomes part of the same shared map of reality that includes Earth, the Sun, and the galaxies nearby. This is one of the quiet messages such discoveries carry. The universe does not organise itself around human relevance. It does not place its most extreme, most powerful or most massive objects near where we happen to live. They are scattered, shaped by conditions that have nothing to do with observation or attention. From that perspective, place in the cosmos is not about location. It is about relationship. The relationship is not physical in the sense of proximity. It is informational. Light travels. Signals carry patterns. Instruments collect and decode them. Minds interpret what they mean. TON 618 becomes part of human awareness not because it is close, but because the universe allows its history to be read across enormous distances. This changes the idea of what it means to be somewhere in the cosmos. Presence is not just about being in a particular region of space. It is about being part of a network of information exchange that spans the observable universe. From Earth, light from TON 618 arrives after a journey of more than 10 billion years. That light carries with it a snapshot of conditions from a time long before the planet itself was fully formed. So when it is observed, two very different moments in cosmic history overlap in a single act of measurement. In that sense, human observers are not just located in space, they are positioned in time. They stand at a point where signals from many different eras converge. This convergence creates a kind of temporal crossroads. The night sky becomes a record, not just of where things are, but of when they were. TON 618 contributes to that record by adding a chapter from an era when the universe was young, dense, and more actively building massive structures. So one message about place is that humans occupy a moment in cosmic history where looking outward is also looking backward. The universe is not a single, unified now. It is a layered collection of pasts, all visible at once. That idea alone can shift perspective. Another way this discovery speaks to place is through contrast. TON 618 represents an extreme of mass and energy. It is one of the largest known concentrations of matter in a single object. Its quasar can outshine entire galaxies. Its gravitational influence shapes the structure of its surroundings on enormous scales. Now compare that to Earth. The planet is small, light, and fragile by cosmic standards. Its gravity is weak compared to that of a star, let alone a black hole. Its influence does not extend beyond its immediate neighbourhood, and yet Earth is one of the few known places where matter has organised itself into systems capable of reflecting on the universe. This contrast highlights a subtle distinction between physical significance and experiential significance. TON 618 is physically significant. It is a major player in the dynamics of its region of the universe. It shapes galaxies and energy flows. Earth, in comparison, is physically insignificant on cosmic scales. But Earth is experientially significant. It is a place where the universe has become aware of itself, at least in a small, localized way. That awareness does not change the mass of TON 618 or the brightness of its quasar. It does not alter the paths of galaxies or the expansion of space. But it does change the meaning of those things, because meaning is not a physical property, it is a relational one. So another message about place is that significance does not always track with size, mass, or power. It can emerge from complexity, organisation, and connection. TON 618 also speaks to the idea of rarity. Objects like this are not common. They exist at the upper end of distributions. They represent outcomes that require specific conditions and long periods of growth. Earth, in a different way, may also be rare. It is one of the few known environments that supports life, and the only one known to support observers capable of building instruments like James Webb. So there is an interesting symmetry here. At one extreme, there is a black hole that pushes the limits of how massive a single object can be. At another, there is a planet that pushes the limits of how complex and reflective a small object can be. Both are products of the same universe, governed by the same physical laws. This symmetry suggests that place in the cosmos is not about being at the centre of a map or the top of a hierarchy. It is about being part of a range of outcomes that spans from the very small and delicate to the very large and powerful. TON 618 also invites reflection on scale in a more personal sense. When people encounter numbers like billions of light years or tens of billions of solar masses, there is often an initial reaction of smallness. It can feel as though individual lives are insignificant in the face of such vastness. But there is another way to look at it. The ability to understand, even partially, something like TON 618 is itself remarkable. It requires not just a single mind, but a long chain of shared knowledge, tools, and collaboration across cultures and generations. The discovery and study of such an object is not the work of one person, or even one era. It is the result of centuries of accumulated insight into mathematics, physics, engineering, and observation. So while any single human is small compared to the universe, the collective effort of humanity can reach across cosmic distances, at least in terms of understanding. That collective reach becomes part of what place means. It is not just where a species lives, but what it is capable of perceiving and interpreting. TON 618, in this sense, becomes part of the extended environment of human awareness. It is not physically nearby, but it is cognitively present. Another dimension of place that this discovery touches on is the idea of universality. The same laws of physics that govern the behaviour of matter on Earth govern the behaviour of matter around TON 618. Gravity works the same way. Light follows the same rules. Atoms behave in the same patterns. This universality means that despite the enormous differences in scale and environment, there is a continuity between the everyday world and the most extreme cosmic structures. That continuity can be grounding. It suggests that humans are not outsiders in a strange and alien universe. They are participants in a system that operates according to principles that can be learned, tested, and understood. TON 618 does not require a new kind of physics to exist. It requires the same physics, applied in a regime that is far from everyday conditions. So another message about place is that the universe is not divided into a familiar human domain and an incomprehensible alien domain. It is one connected system, experienced at different scales. There is also a message about timing. The fact that TON 618 is observed as it was billions of years ago means that human observers are, in a sense, late arrivals. The universe spent a long time building structures like this before there were eyes to see them. That can be interpreted in different ways. One view is that life and consciousness are rare and fragile outcomes that emerge only after long periods of cosmic preparation. The universe had to form stars, then heavier elements, then planets, then stable environments, before something like a thinking species could arise. From that perspective, Earth's place in the cosmos is not central, but it is special in terms of timing. It exists at a moment when the universe is old enough to have produced complex structures, but not so old that stars and galaxies have faded away. TON 618, observed in its earlier phase, becomes part of that story. It represents a stage in cosmic evolution that set the conditions for everything that followed, including the formation of the elements that make up planets and living organisms. Another angle on place comes from thinking about perspective. TON 618 does not know it is being observed. It does not change its behaviour because it has become part of a human narrative. It continues to exist and evolve according to the same processes it always has. This one-sided relationship highlights the asymmetry between observer and observed. Humans look outward. The universe does not look back, at least not in any intentional sense. So, place in the cosmos includes this role as observer. It is a role that is not guaranteed. It is contingent on the existence of minds, tools, and curiosity. TON 618 becomes meaningful in a human context, because it is part of a story that humans tell about the universe and their relationship to it. Another subtle effect of discoveries like this is how they influence imagination. Before objects like TON 618 were known, the upper limits of cosmic size and power were different in the human mind. There were still large things, but the range of what seemed plausible was narrower. As new extremes are discovered, that range expands. This does not just change scientific models, it changes the mental landscape in which people think about the universe. The cosmos becomes a place where outcomes can be more varied, more extreme, and more surprising than previously assumed. That expanded sense of possibility feeds back into how humans think about their own potential and their own future. If the universe can produce structures as massive and powerful as TON 618, perhaps it can also produce forms of complexity and organisation that have not yet been imagined. Another message about place relates to humility. TON 618 makes it clear that human concerns, cultures, and histories occupy a very small region of space and time. Civilizations rise and fall on timescales that are barely noticeable compared to the lifespan of a galaxy or a black hole. This does not mean those concerns are meaningless. It means they are local. In a universe as large and old as this, locality becomes an important concept, meaning value and purpose are not written into the large-scale structure of the cosmos. They are generated within smaller systems, within societies, within individual lives. So place in the cosmos is not something that is assigned from above. It is something that is constructed from within. TON 618 does not define what matters to humans. Humans decide what matters to them, even while acknowledging the larger context in which they exist. There is also a message about continuity. The atoms that make up human bodies were formed in stars. Those stars lived and died in galaxies. Those galaxies evolved in a universe shaped by gravity, expansion, and the distribution of matter. TON 618 is part of that same chain. It is not separate from the material that eventually became planets and people. It is part of the same cosmic circulation of matter and energy. So in a very literal sense, the existence of such a black hole is connected, through long and complex pathways, to the existence of observers. This connection is not direct, but it is real. Another way to think about this is in terms of shared origin. Both TON 618 and Earth trace their history back to the same early universe. They emerge from the same initial conditions shaped by the same physical laws. They represent very different outcomes of that shared beginning. One outcome is a massive black hole at the centre of a distant galaxy, shaping its environment through gravity and energy. Another outcome is a small planet with liquid water, a stable climate, and a biosphere capable of producing intelligence. Both are expressions of the same underlying processes. So, place in the cosmos can be seen not as a fixed position on a map, but as a role within a broader pattern of emergence. TON 618 plays one role, Earth plays another. Neither is more cosmic than the other. They are simply different. As this perspective settles in, the discovery of such an extreme object can begin to feel less like a reminder of smallness and more like an invitation to connection. It invites a view of the universe as a network of relationships rather than a hierarchy of importance. From that view, being human in the cosmos means being part of a system that is capable of producing both immense physical structures and intricate patterns of thought and awareness. TON 618 stands as a marker of the first. Human observers stand as examples of the second, and between them lies a vast, continuous landscape of matter, energy, space and time, all governed by the same quiet rules, all participating in the same ongoing process. As attention gradually turns from this broader perspective back toward the future of discovery, there is a sense that objects like TON 618 are not endpoints in understanding, but signposts. They show where current knowledge stretches thin. They point toward questions that remain open. They guide the design of new instruments, new theories, and new ways of looking. So the place of TON 618 in the cosmos is not just as a distant giant. It is also as a reference point for curiosity. And the place of humanity in the cosmos, in turn, is not just as a small, isolated observer, but as a participant in a long, unfolding conversation with the universe, one that continues each time a new signal is caught, a new pattern is recognized, and a new question begins to take shape, carrying the story forward rather than bringing it to a close. After spending so much time near the limits of scale, there is a natural pull to move back inward, not toward a specific place, but toward a quieter state of attention. The edge that TON 618 represents is not a physical boundary you can cross and return from. It is a conceptual edge, where familiar reference points thin out, and the universe begins to feel less like a collection of objects, and more like a continuous unfolding process. Drifting back from that edge does not mean leaving it behind. It means carrying what it revealed into a calmer, more grounded frame of mind. The silence that surrounds TON 618 is not the absence of activity. It is the absence of immediacy. Everything happening there unfolds on timescales and distances that do not intersect with human senses directly. No sound travels through space. No vibration reaches outward to announce what gravity is doing near the event horizon. There is only light, stretched thin by distance and time, arriving softly, billions of years after it was emitted. That delayed arrival is part of the silence. When you consider this, it becomes clear that the universe does not rush to be known. It allows discovery, but only on its own terms. Signals move at fixed speeds. Information is limited by distance. Patience is built into the structure of reality itself. TON 618 embodies that patience. It grew slowly, over immense spans of time, gathering matter grain by grain, cloud by cloud, star by star. Its influence accumulated, its presence deepened. There was no single moment when it suddenly became what it is. There was only continuation. That continuity mirrors the way understanding develops as well. No single observation revealed the full picture. No single telescope solved the puzzle. Instead, knowledge arrived incrementally. First a bright point in the sky, then a quasar, then estimates of mass, then refinements, then Webb, adding texture, context, and depth. At each stage, the picture became slightly clearer but never complete. Drifting back from the edge means accepting that incompleteness without frustration. It means recognizing that not knowing everything is not a failure of understanding, but a natural consequence of scale. There is a tendency, especially when dealing with extremes, to look for final statements. The biggest, the farthest, the most massive. But the universe does not seem particularly interested in finality. It produces ranges, not absolutes. It allows records to be broken, categories to stretch, and expectations to shift. TON 618 may not remain the largest known black hole forever. Somewhere, perhaps even farther away, there may be another that exceeds it. Or perhaps not. The point is not whether this object holds a permanent record. The point is what it reveals about possibility. Carrying the silence with you means letting that idea settle without needing to resolve it. It means allowing space for uncertainty, not as a gap to be filled immediately, but as a condition that invites continued observation. In everyday life, silence is often uncomfortable. It can feel like a pause that needs to be filled, a moment where something should be happening. In the context of the cosmos, silence is the default. It is the background against which rare signals stand out. TON 618 does not fill the universe with noise. It emits energy, yes, but that energy disperses. It fades. It blends into the general glow of distant galaxies. Most of space remains dark and quiet. This contrast can be grounding. After encountering something so large and distant, returning attention to smaller, more immediate scales can feel different. The weight of everyday concerns shifts slightly, not because they disappear, but because they are seen within a broader context. The universe does not diminish local experience, it frames it. From the perspective of TON 618, Earth is insignificant. From the perspective of life on Earth, Earth is everything. Both perspectives can exist at once without contradiction. Drifting back from the edge means holding both views without forcing one to cancel the other. There's also something important about the direction of this movement. You are not falling away from knowledge, you are returning with it. The silence carried back is not empty, it is informed. It holds the awareness that the universe is vast, structured, patient, and capable of outcomes that exceed intuition. That awareness does not need to be active all the time. It does not need to dominate thought. It can rest quietly in the background, available when needed. This is similar to how deep experiences work in general. They do not remain vivid at every moment, but they leave traces. They alter perspective in subtle ways. TON 618 leaves that kind of trace. It suggests that scale is not something to be mastered mentally in full detail. It is something to be approached, acknowledged, and then stepped back from, carrying only what is useful. What is useful, in this case, is the reminder that the universe operates over ranges far beyond human planning. But it also produces environments where planning, reflection, and rest are possible. The same physics that allows a black hole to grow to tens of billions of solar masses also allows atoms to form stable molecules, planets to maintain long-term climates, and brains to develop patterns of thought. These are not separate stories. They are different expressions of the same underlying order. As attention settles, the idea of the edge itself begins to soften. The edge was never a sharp boundary. It was a region where familiar language became less effective. Moving away from it does not mean returning to ignorance. It means choosing a scale that fits the moment. Right now, that scale is quieter. The silence carried back from TON 618 is not the silence of emptiness. It is the silence of continuity. Things are happening, but they do not require immediate response. Black holes continue to grow or fade. Galaxies continue to merge. Light continues to travel. None of this depends on observation to proceed. That independence can be strangely calming. It suggests that the universe is not waiting. It is not demanding attention. It simply unfolds. From within that unfolding, moments of awareness appear. Observations happen, questions arise, answers form, partially. Then the focus shifts again. This rhythm between attention and release mirrors natural processes on smaller scales. Breathing in and out, tension and rest, activity and sleep. The study of something like TON 618 fits into that rhythm as well. There is a time for looking outward, measuring, comparing, questioning, and there is a time for letting those thoughts settle. Drifting back does not erase the knowledge gained, it integrates it. As the mind returns from the far reaches of cosmic scale, the silence remains as a background condition, a reminder that not everything needs to be resolved, categorized, or concluded. The universe does not offer neat endings, it offers continuity. TON 618, for all its size and power, is not a conclusion to the story of black holes. It is part of a distribution, part of a process, part of an era. Understanding that can take pressure off the need for closure. There is always more to observe. There are always refinements to be made. New instruments will gather new data. Models will shift. Estimates will tighten or expand. That ongoing nature is not a flaw. It is the shape of discovery. Carrying the silence with you means allowing that openness to remain. It means letting the idea of the universe as an active, evolving system sit quietly alongside daily routines and familiar surroundings. A room does not feel smaller because the universe is large. A moment of rest does not feel less real because black holes exist. These scales do not compete, they coexist. The silence from the edge reminds you of that coexistence. It suggests that meaning does not need to be proportional to size or distance. It can arise locally even while acknowledging vastness. As attention continues to drift, there is no need to summarize everything that has been explored. The mind does not retain understanding by listing facts. It retains it through patterns and impressions. The pattern here is one of scale layered on scale, of relationships rather than absolutes, of patience rather than urgency. Ton 618 becomes one node in that pattern, not a destination, not a final word, but a reference that gently stretches perspective. And as that perspective stretches, then relaxes, the silence settles into a comfortable presence. Not empty, not heavy, simply there. The universe continues as it always has, whether observed or not, and within that continuation, moments of awareness come and go, carrying with them traces of distant light, ancient gravity, and the quiet understanding that even at the farthest edges of what can be known, there is no sharp boundary where meaning ends, only a gradual fade into a wider, ongoing story that does not conclude, but keeps unfolding, calmly, patiently, and without needing to announce itself.